Good day, everyone. Welcome to the fifth webinar of the A-GaME Winter Webinar Series. We have a twofer for you today. We have geophysical methods starting off with electrical methods. So focusing this first session, 90-minute session on electrical methods, talking about some of the fundamental considerations of electrical methods and applying those to our site characterization efforts. Recognizing also that when we're talking about the case histories as we get into this, that on the bigger picture of site characterization, having that full understanding of what our objectives are. We use more than one method typically. So, that is, part of the rational process of using methods that are appropriate and that will help us build that model and drill down. So you'll see electrical methods as sort of the primary backbone of this discussion, especially talking about the fundamentals, but we will be talking about some other methods mixed in with the case histories as well. We will have time at the end of this session for question and answers. We have a number of speakers and panelists who are primarily most speakers for both sessions, but they are going to be here for both of the sessions today to answer questions. So with that, I am going to start the next session. So Mike, if you want to go ahead and get your presentation loaded, I'll stop sharing my screen and introduce our first speaker. Michael Howley is with Hager-Richter. He has his bachelor's and master's degree in geology from the University of New Hampshire with extensive coursework focused on near surface applied geophysics. He's been with Hager-Richter since 2010 and has participated in all aspects of Hager-Richter's field projects in engineering, geology, and geophysics for sites across the eastern United States. He's Hager-Richter's technical lead for resistivity surveys and is a professional geologist in New Hampshire and in New York. With that, Mike, you take it away.
All right. Thank you, Ben, and thank you to everyone who are attending today. My presentation is going to focus on the electrical geophysical methods and their application to transportation projects. Before I get into the electrical methods, here's a quick plug for the benefits of using geophysics and exploration. Non and minimally invasive with less environmental impact, especially compared to drilling. Can reduce drilling costs by interpolating between boreholes based on data, not just blind interpolation. Improve confidence in the geotechnical characterization and establishes a more reliable basis for design and construction, and accelerated project delivery. Many construction delays are attributed to inadequate knowledge of subsurface conditions. Well-scoped investigation program improves decision-making, constructability, and provides time and cost savings. Here's a brief outline of my presentation. I'm going to introduce three electrical geophysical methods, which are electrical resistivity, induced polarization, and self-potential. I'm going to refer to these usually by their initials. Induced polarization is IP, self-potential is SP. I'm going to briefly describe their basic theory, applications, and limitations, then share some relevant case studies that use these methods. I'll let you know right from the outset that the electrical resistivity is the most applicable to transportation-related projects. Many DOTs and geotechnical consultants already do widely use this method for exploration. The resistivity method relies on the contrast in electric resistivities between different earth materials. Resistivity surveying measures the resistance to the flow of electric current in the subsurface. Typical applications relative to transportation projects are detection of voids, karst features, and tunnels, determining depth of bedrock, detecting the presence of peat or clay layers, and determining unknown depths of foundations. Other applications of the method exist, but I'm not going to focus on them for this presentation. The resistivity of earth materials is controlled by a combination of water content, which is the most important control, porosity and permeability, pore fluid chemistry, is the groundwater fresh or saline, resistivity of the soil and rocks, this is an inherent physical property, and temperature. Acquiring data in relatively small areas along survey lines or grids can reduce the number of variables and allows detection of patterns or anomalies that correspond to the features of interest. The resistivity of earth materials is measured in ohm meters. As you can see in the chart, there's significant overlap in the resistivity of different lithologies. The most conductive materials are sulfides, down the low end, low resistivity, high conductivity. And the most resistive are unweathered, crystalline, igneous, and metamorphic rock, limestone, and permafrost. The resistivity method utilizes the contrast and the resistivities of dissimilar materials to detect their occurrence in the subsurface. For example, clays have a different resistivity range than sand and gravels. We use this to allow detection of those features. Resistivity data can be acquired as one-dimensional vertical electrical soundings, two-dimensional resistivity profiles, three-dimensional resistivity grids, or time-lapse measurements of 2D or 3D data. The images show the basic configuration of a resistivity survey. Current is injected through two electrodes. In this cartoon, these are the two current electrodes on the outside. Voltage or potential are measured from two other electrodes. The figure on the right shows three of the most common arrays for acquisition of resistivity data: the Schlumberger, Wenner, and dipole-dipole array. The differences between the array types are the configuration and spacing of the electrodes. Vertical electric soundings, 1D data, have been acquired since the 1930s, but due to equipment limitations and the long times required for acquisition, the method fell out of favor for exploration until the advent of automated resistivity systems. A modern automated resistivity system can measure resistivity at several positions at the same time. Measurements made at increasing distance from the current injection site are measuring resistivity at theoretical deeper depths. As shown in the image on the right, current is being injected at this location. Potential is measured at these locations on the surface that correspond to deeper depths in the subsurface. This is a dipole-dipole survey schematic. This is an image of a 2D resistivity survey. The equipment is sitting, there's 56 electrodes connected by a multi-core cable. The electrodes are 14-inch long stainless steel rods that are driven into the ground and connected to the cable. Using multi-electrode automated resistivity systems, 2D resistivity profiles can be acquired over large distances in a single field day. The schematic shows the current injection site, I, the voltage measurement site, V, and the theoretical depth of the measurement, shown in that black box. The measured resistivity is the apparent resistivity at that location because of the other influences because of the influence of the other material through which the current flows. It's the effective weighted resistivity of all the materials through which the injected current flows. Use some photos of 2D resistivity profiles being acquired. As I mentioned, the environmental impact of this type of survey is far less than that of drilling. The equipment is hand or ATV portable, and acquisition of up to 1,000-foot long resistivity profile requires about 2 to 3 field hours. Very important part of designing a resistivity survey is knowing prior to the survey the target depth, size, and resistivity contrast. The inter-electrode spacing is adjusted to maximize the likelihood of detection while maintaining productivity. Rule of thumb for depth investigation is approximately 10 times your electrode spacing is your maximum effective depth investigation. It does vary with array type and the resistivity of the soils in the subsurface. The measured apparent resistivity is used to create an inverted resistivity profile. The top panel is the measured apparent resistivity. The middle panel is the calculated resistivity pseudosection, and the bottom is the inverted resistivity profile, similar to a cross-section, a geologic cross-section. This resistivity survey was acquired with 10-foot electrode spacing, 56 electrodes, and 2 rolls of the electrode cables. The inverted resistivity section is trimmed at 45 degrees at the ends to remove data that is not well constrained. This is the resulting inverted resistivity section with an interpretation of the data shown in the previous slide. The modeled resistivity is plotted on a log scale, and the color scales are adjusted. The limits of the color scale are adjusted to highlight the features of interest. This data was acquired in an area of high resistivity crystalline bedrock. Conductive features present within the bedrock, shown by the long dashed lines, are interpreted to be water-filled, clay-filled, or mineralized clay fractures. Primary limitation of a two-dimensional resistivity survey is that when the inverted resistivity section is calculated, the apparent resistivity measurement is assumed to be directly under the profile line. In reality, the area of an apparent resistivity measurement is more like a flashlight shining downward. Resistivity changes off the line will impact the apparent resistivity measurements along a 2D profile. The resistivity method does give a good picture of the electrical structure of the subsurface, but to get a better understanding, we have to go to a 3-dimensional resistivity survey. 3D resistivity surveys measure resistivity from a series of either closely spaced 2D profiles, shown in the image on the left. This is called a pseudo 3D survey, or a grid of electrodes shown in the photo and image on the right. This is a true 3D survey. 3D resistivity has the ability to resolve the true shapes of anomalies, such as karst features, to calculate volumes of subsurface materials. The survey arrangement on the left was used to map depth of competent bedrock in an area where the property owner would not allow us to use an active seismic source. It was a pasture and didn't want to disturb the sheep. The survey on the right was a demonstration conducted by the equipment manufacturer at a conference to detect a paleo channel feeding a spring house. You can see the interpreted location of the paleo channel in the inverted 3D dataset right there. Some common limitations of the resistivity method are surface conditions. You do need soil present at the ground surface of planting electrodes. Very dry surfaces or armored slopes are often not appropriate. This resistivity data can be acquired through asphalt pavement. However, the impermeable nature of pavement often makes the subsurface very dry and requires significant amounts of water to get the electrodes to have electrical contact with the subsurface. Number 2, subsurface conditions, subsurface conductive utilities and structures can create a short circuit of measurements. It causes anomalies in the data that are not due to resistivity changes in the subsurface. In my experience, parallel subsurface conductive feature, such as a water line, located within about half the line length, can negatively impact the data. Guardrails that have metal posts that penetrate the water table can create short circuits. This is not consistent. Something they often have to try and see if it works. Number 3, the resistivity of the subsurface and the electrical resistivity contrast of the target. A strong enough resistivity contrast between the target and surrounding materials is needed to resolve the target. For example, a granite boulder in a till matrix is not a large enough contrast to be detected, usually. 4, detection is not identification. As with most geophysical methods, this is detection of an anomaly. It is not identification of what that anomaly is. Number 5, the trade-off of depth investigation versus lateral and vertical resolution. As I mentioned earlier, knowledge of the size and depth of the target is needed to tailor the survey to that situation. And number 6, you do need ground truth in the form of boring control. In the absence of any boring control, geophysicists only talk about presence of anomalies. They don't associate them with conditions on the ground. The second method I'm going to discuss is induced polarization. The IP method measures the ability of the earth materials to maintain current flow for a short amount of time after the applied current is terminated. This is the time domain version of IP. In the diagram, time on the horizontal axis, you have a voltage that turn off that voltage. The residual voltage that remains is measured by the instrument. This is the chargeability anomaly. The other version of IP surveying is where the method detects areas where the resistivity decreases as the frequency of the applied current is increased. This is the frequency domain version of IP. And the orange circle shows the phase shift of an alternating current due to a varying frequency. The property measured is called chargeability and is variable from one site to the next. Chargeability of in situ earth materials is primarily a function of mineralogy. IP surveys are conducted similar to 2D resistivity profiles, and resistivity and IP data are always acquired together. The results of IP surveys are presented as pseudosections or inverted chargeability sections. The IP method is widely used in exploration for ore bodies, primarily for disseminated sulfide deposits containing metals. IP is also used in groundwater exploration, locating clay pockets within host rocks, and detecting unknown or forgotten man-made structures. The reference is to a Texas DOT sponsored project that used resistivity and IP to detect depth of known pile-supported foundations. Third method I'm going to discuss is the self-potential method, or SP method. The method involves the measurement of naturally occurring electric potentials between 2 points on the Earth's surface. The potentials are usually on the order of 10 to 100 millivolts. The method's also known as streaming potential and spontaneous potential, depending on the process that creates the potential. Luckily, they all have the same initials, so we just refer to it as SP. The most important process relative to transportation projects is the flow of fluids through porous materials, or seepage. The figure shows the magnitude of an SP anomaly that decreases as you're moving over an area of flowing water. The cause of SP anomalies generated in the subsurface is not well understood. SP is a qualitative method that can be used to locate anomalies, but does not quantify the size, shape, density, or electrical properties of the causative body. 2 applications of SP surveying that are most relevant to transportation projects are leakage of a reservoir within the foundation of a dam and movement of water through a karst system. The graphic on the right shows streaming current proportional to water flow moving downhill, the balancing negative charge moving back uphill, and the corresponding SP anomaly that would be found. SP data are acquired along lines or in a grid across the area of the expected anomaly. Measurements are made with non-polarizing electrodes to eliminate contact voltages due to moisture. Non-polarizing electrodes are usually constructed of a copper rod immersed in a bath of copper sulfate solution with an unglazed ceramic tip. The ceramic tip allows the solution to slowly trickle out through the bottom of the electrode. The photo on the left shows two non-polarizing electrodes that are installed at depth about 6 inches below ground surface. We found that being in contact with vegetation does create small voltages that will interfere with the true SP anomaly. And the figure on the right shows an area of a SP survey that was conducted on the downstream side of a earthen dam. There's two methods of conducting an SP survey. The potential is either measured between a fixed electrode and a roving electrode. This is called the fixed base method, or between two electrodes at constant spacing. This is the gradient method. A fixed position has to be remeasured to allow corrections for variations due to natural and anthropogenic influences. Limitations of the SP method. Natural variations in SP can occur due to varying soil types, soil moisture, and chemistry. Also, geomagnetic storms. The varying magnetic field strength can induce currents in the subsurface or in the cables that are used to measure SP data. Thunderstorms within up to 50 miles away can cause variations and potentials in the ground. And then the anthropogenic influences, infrastructure, power lines, buried utilities can leak voltage into the ground that cause SP anomalies far greater than that created by flowing water. The method does require direct contact with soils, so again, not appropriate for paved surfaces, armored or rocky surfaces. The advantage of SP is that it's an excellent reconnaissance tool of an area to locate areas of water flow, followed by a resistivity survey to identify or image the structures controlling that flow. All right, back to the outline. I'm going to move on to a couple of transportation-related case studies that use these methods. First case study is, the objective was to detect blast rock fill in an elevated roadway. This was in Merrimack, New Hampshire, along the Everett Turnpike. It was conducted for New Hampshire Department of Transportation. They said the objective was to detect the possible presence of blast rock fill above a 60-inch existing culvert. Planned replacement by pipe jacking in a 90-inch diameter culvert adjacent to the 60-inch. The pipe jacking cannot penetrate blast rock fill that may be present. The methods employed were multi-channel analysis of surface waves, MASW, that is going to be discussed, I think, in the second session, as well as resistivity imaging. So the general location of the site. This is a 2-lane each direction highway. It's one of 2 major highways connecting New Hampshire and Massachusetts. This is a site plan showing the southbound on the top, northbound on the bottom. The black line is the existing 60-inch culvert. The gray line is the proposed path of the 90-inch culvert that's going to be pipe jacked in. We acquired 3 survey lines, survey line 1 on the southbound shoulder, survey line 2 on the northbound side between the roadway and an on-ramp, survey line 3 in the median along the concrete barrier. We acquired MASW on all 3 lines and resistivity on survey line 1 and survey line 2 only. The asphalt was found to be 12 inches plus thick in this area, and installing the electrodes through that asphalt was not possible. 2 photos of the acquisition. Photo on the left is the MASW survey conducted along the barrier in the median. The survey on the right shows both the MASW line and the resistivity profile that were required between the northbound travel lane and the on-ramp that's over here off to the right. All right, so this is the results of survey line 1 that was acquired on the southbound shoulder. Inverted resistivity profile showing the resistivity structure of the subsurface, as well as the MASW profile that was acquired in the same area. This white dot here and here is the approximate location of the existing 60-inch culvert. We interpret the results of the resistivity survey to show high resistivity anomalies that are interpreted to be possible blast rock fill areas present above fine-grained native soils that are a low resistivity anomaly. That's supported by the MASW results that show pockets of high shear wave velocity material present at about the same depth and location. The difference between the resistivity and MASW is the native soils that are present below the existing culvert are a low resistivity anomaly. It's a fine-grained sand and silt, water saturated, whereas that is a high shear wave velocity anomaly. Survey line 2, this was acquired on the northbound side between the travel lane and the on-ramp. We do have boring control, a boring that was installed at the location of the proposed culvert that encountered medium to fine-grained fill over fine-grained native soils. 2 smaller areas of possible blast rock fill indicated by high resistivity anomalies in the resistivity data. Similarly located high shear wave velocity anomalies that are indicated or interpreted to be blast rock fill at the same locations. Again, the lower resistivity at depth is due to the water saturated fine-grained native soils. Based on the results of these 2 profiles, we interpret that blast rock fill is likely present on the southbound side of the elevated highway, but discontinuous pockets or boulders present in the fill on the northbound side. The second case study I'm going to present is a seepage investigation at Moore Dam on the New Hampshire-Vermont border. The objectives of this survey were to locate water flow and select locations for borings and piezometers, as well as detect structures that may be acting as conduits for the seepage. 2 methods used were SP and resistivity imaging. The location of the site is right on the New Hampshire to the bottom, Vermont to the top. It impounds the Moore Reservoir, which is approximately 4,000 acre reservoir. It's an active hydroelectric facility. This is a view looking north towards the Vermont side. It's a clay cored earthen dam. There's a tow drain here at the bottom of the 2-to-1 slope, terrace, another slope, and another terrace. There's seepage that is evident on both of the terrace levels. The question we were trying to answer is that seepage coming from the hillside to the north, or is that coming through the embankment dam, indicating issues with the structure? It's an image of seepage on the lowest terrace. There's a significant amount of water coming through. After this image was taken, a geotechnical investigation was started that involved the geophysical methods that I mentioned. So we conducted an SP survey over 8 field days on a 20 by 20 grid in a approximately 600 by 900 foot area. We used the fixed base station SP method. At each of these dots, the SP values were measured. The data were adjusted for both fluctuations within a field day and between field days relative to a fixed base station. SP data presented as a color contour plot of the measured SP value between an infant electrode and a roving electrode for each data station. For Moore Dam, anomalously low potential differences, cooler colors, purples and blues, indicate flow in the subsurface. Such areas of low potentials are shown as, areas of high potential difference, the red to orange and yellow color indicate areas of little or no flow. Based on the SP survey results, 12 resistivity survey lines were acquired across the areas of flow indicated. The resistivity was acquired using 56 electrodes, a variable inter-electrode spacing depending on the length of the line and the depth of the target depth of the structure. These are the inverted resistivity profiles for 6 of those 12 lines that I just showed you. As you can see, some known structures were detected, known rock drains, as well as several unidentified features shown here and here. These are low resistivity anomalies indicating either increased water presence in these areas or more conductive soils. And the other series of 6 resistivity profiles showing similar features, some known rock drain locations, as well as some unidentified or previously unidentified features. Put several of these together into a 2-dimensional fence diagram. The seepage paths mapped by the SP correlate well with known structures as well as some previously unknown structures. The end result that was determined from this is that the toe drain at the base of the 2-to-1 slope is not capturing all of the flow in the known rock drains. Rather, it's bypassing that structure and then flowing down across the terrace and creating the seepage that's observed down at the base level. This is not strictly a transportation project. However, it is a good analog for using SP to detect areas of flow, followed by resistivity to detect the structures controlling flow. This would be similar to water flow into a karst system. And that is all I have for a presentation. And I think I'm going to do questions at the end.
Excellent. Thank you very much, Mike. We did have one question that did come in. You had referred to a rule of thumb, I think, for the depth of investigation. So the question was, what was that rule of thumb that you mentioned?
Sure. The rule of thumb that we use for our system is a 56 electrode system. They can go up to 112 from this equipment manufacturer. For depth investigation using either dipole-dipole or Schlumberger array, it's roughly 10 times your electrode spacing. So if you have 56 electrodes at 10 feet, your depth investigation would be roughly 100 feet. The resolution is also dependent on that electrode spacing. You would be able to resolve something that's approximately half of your electrode spacing.
Okay, very good. Yeah, I had heard as a rule of thumb also, yeah, if you're looking for, you know, a certain depth, your total length needs to be at least 3 times. Is that hold water, or?
It does. Where you can use different configurations, different number of cables and switch boxes to increase your total line length. The total number of electrodes isn't as important as the distance between your electrodes. You are limited for how far you can detect your injected current. If you have a 1,000-foot long line, you're not going to detect 300 feet down, very likely.
Right. Gotcha. Very good. Well, thank you very much, Mike. Great presentation. Our next speaker is Clint Wood, and Clint, you can go ahead and get your screen ready. Dr. Clint Wood is an associate professor in the Department of Civil Engineering at the University of Arkansas. He received his bachelor's and master's at the University of Arkansas and his PhD at the University of Texas, Austin. His research focuses on geotechnical earthquake engineering and non-destructive infrastructure evaluation, with an emphasis on dynamic site characterization using surface waves methods. He's published over 60 journal articles and conference publications focusing on topics from surface waves, liquefaction, earthquake side effects, levee evaluations, and topographic amplifications. He's also working closely with Arkansas DOT on their A-GaME and has done quite a bit of work there. So Clint, I will turn it over to you, sir.
Okay. Are we good on the screen and everything? Just to make sure.
I can see it. Yep.
All right. So in this presentation, what I wanted to do is kind of change a little bit from just being strictly resistivity to showing kind of the benefits of combining resistivity and seismic methods. So just not choosing one, because that's often not done, just like the stuff Mike showed. You know, a lot of times we want to use multiple methods so that we can really harness the advantages of those different methods for a particular application. So this is going to be a case study from Ozarks, Arkansas that I've worked on with the Arkansas Department of Transportation. So again, the case history helps demonstrate how these two methods, so resistivity and seismic methods, can be combined to harness their strengths and, you know, get rid of some of the limitations of each one of them. So the case history is a project that's part of the validation phase of a research project we're working on with RDOT, where we validate these methods, geophysical methods, for current and future RDOT projects. The goal of the testing was to provide detailed information on the subsurface conditions of this slide. So particularly bedrock depth and then water conditions. So where is the water moving in the slope or pooling, or where were saturated layers? So that we can aid in the repair of the slope and come up with something that would work in this particular case. So this is where Ozarks is. It's in the Ozark Mountains of Arkansas. So for this particular project, this is along Interstate I-40. So this is a major thoroughfare in Arkansas. And this has had stability issues along the 400 or 500 foot section of the westbound lane since the 1970s. And, you know, over the years of, you know, up to the 1980s, they were redressing the slope to try to repair it. And then a drainage system in the early 80s was modified to try to remove the water, get the water away from the slope, both with surface drainage and subsurface drainage, try to move this water away from the area that is causing the failure of this slope. And in 1983, they excavated clay materials along the toe of the slope and replaced it with granular material and try to buttress the slope. So these are kind of common things that are done for these particular slides to try to address them in a relatively inexpensive way. And in some cases, this works pretty well. In some cases, it doesn't. So this is the area after it. This is the slope that kind of comes out. All these pictures were taken in 2018 after a repair that we're going to talk about that wasn't necessarily totally successful. So it's about a 3-to-1 slope in this case. So not an extremely steep slope, but in 2018, several cracks that extend across the roadway and then cracks over here in section 2 that come across were formed and are leading to this instability in the slope. So we haven't had a complete failure, but we're definitely having distress in the slope that's going to eventually lead to some type of failure. So in 2016, it was decided to do a more comprehensive subsurface investigation program where 18 borings with SPT measurements were taken mostly along the top of the slope and on the other side of the road, but then a roadway was cut in and done closer to the toe of the slope. The toe of the slope's actually down here at the bottom, but kind of at more of a midpoint of the slope, and indicated, you know, moist clay to sandy clay with rock fragments. Blow counts varied significantly, likely due to the rock fragments and other things in the subsurface, from 30 to 40 to 5 to 15. And it was underlined by a shale bedrock where, you know, somewhere between 35 and 60 feet below the surface, depending on where you were on the project. They also installed a number of inclinometers. So 2 up here at the top and 2 up here at the bottom. These inclinometers showed that basically the slope was slipping along the bedrock layer. That even up at the top of the surface where it was 65 feet deep, we were seeing slip along that section. And then once we got down here to the bottom of the slope, we were still seeing slip along the bedrock interface. And generally in that interface, blow counts were around about 10. So this information was taken, and then there's kind of a lack of information in a couple of different places in the slope. So the mid part of the slope, and then the very bottom, the toe of the slope. There wasn't much information available from the particular borings that they did. So in 2018, the design, along with Hager-Richter, was to install 100 different rock anchors along this section of the slope in 3 different lines. So one major line and then a couple of secondary lines that set through there. So these anchors were installed into the shale bedrock, and they had an anchor block that set along with that. However, in less than a year after this repair, additional movement was observed. So the pictures I showed with the cracking is the additional movement that occurred afterwards. So while this may have prevented a major failure from occurring, it did not prevent the movement from occurring in the slope, that it continued to have slight movements and crack form on there. So it wasn't a satisfactory fix in this case. So as part of the research project, we were brought in to try to help determine what's going on in the subsurface that may be contributing to this slide in the movement and potentially why this fix didn't work in those cases. So we used a couple of different methods. So this is where we're going to get into the combined methods. So multi-channel analysis of surface waves, P-wave refraction, electrical resistivity tomography, and then horizontal to vertical spectral ratio. So a lot of this will be discussed kind of in the fundamentals, but I'm just going to go through a little bit for each method. So MASW is an active surface wave method, utilizes the dispersive properties of surface waves. And those can be Rayleigh or Love, but traditionally Rayleigh waves have dominated the surface wave game, but Love waves are starting to get more and more action in terms of particular sites that they're very good at. Those are generally shallow bedrock sites. So we use these to measure surface wave velocity and then infer shear wave velocity from that. And really the reason we chose MASW on this particular project is because we had shallow saturated soil layers at the surface, and we suspected that those velocities were going to be, the P-wave velocity was going to be saturated velocity, so 5,000 foot per second. And that was going to be very close to the rock velocity. So it was going to be hard to determine the separation between where is rock and where is water in the slope. So MASW overcomes that by using shear wave velocity. We also considered shear wave refraction in this case, but due to the high traffic noise on the project, it was going to be difficult to generate shear waves that propagated the whole length of the array in order to be able to image what the bedrock depth was at the site. So MASW, like most surface waves testing, starts with acquisition, processing to get the dispersion curve that's associated with that, and then some sort of inversion to develop the shear wave velocity profile. And this is really a non-unique issue that you're getting into in getting this shear wave velocity profile, that many different shear wave velocity profiles can fit a particular measured set of data. And this is true of a lot of geophysical methods that you run into. So for this particular project, we used a linear array of 48 4.5 hertz vertical geophones with several roll-alongs in this section, and equals geophone spacing between 1 and 2 meters, 2 meters really along the slope, and 1 meter when we ran down the slope, in order to reduce that vertical issue, because MASW really doesn't take into account vertical changes. So that's kind of a problematic deal. So we weren't sure that it was going to be particularly successful on the project. Source locations were off each end, and then every 4 meters within the array. So we use multiple source offsets in this case. So we analyzed multiple MASW sets from multiple source offsets as a way to mitigate potential near field effects. So that's where you set your source too close to your receivers. And to quantify uncertainty in our measurements, that looking at multiple dispersion curves help you identify potential problems with your data and get better data and understand kind of what your accuracy in this case is. And to analyze the data, we had, a 24 geophone set. So this is similar to kind of how this is set up. So 48 channel array. And then we pick different 24 channel sets and analyze those individually with the appropriate source locations. And we did do Rayleigh and Love wave testing at the start of the project to assess which one produced better dispersion data. In this particular project, the bedrock was both soft enough and deep enough that Rayleigh waves worked very well in this case. There's been many other projects that we've dealt with that love waves work a lot better in those cases, in these shallow bedrock sites. So getting into the analysis, so all the surface wave methods, and particularly MASW, have to use some type of 2D transform to go from our time-space domain, so our time records, to some other domain like this FK, so frequency wave number. We primarily use our frequency domain beamformer analysis, but we compare it to other transformation methods. And recent work that we've done in this particular area has shown that all these methods of transforming it, whether it's frequency domain, beamformer, FK, phase shift, or tau-p, they can produce different data. And up until now, most people have assumed they give you the exact same answer. And you know, in this particular location, and we've seen it at other shallow bedrock sites, phase shift does not perform as well as other methods. And that's unfortunate because it's used in a lot of software out there. So that's one thing to note. If you end up using this MASW a lot and you get poor dispersion information, you may try a different transformation method, and it may significantly improve your data quality as a result of that, especially at these shallow bedrock sites. At soft and normally dispersive sites, it doesn't really make any difference which one you use. They all give about the same result. But it's these challenging sites, complex sites that really cause problems in surface wave testing. So we take these 24 channel subarrays. We analyze each one of them. We use Geophysics software, which uses a neighborhood search algorithm to try to figure out which one is the best after searching many, many different models. We do a joint inversion with horizontal to vertical spectral ratio. That significantly improves the accuracy of your bedrock depth, because now you've got two model parameters that are trying to fit this data from the subsurface. And when you do that, you improve your accuracy of the final model in this case. So almost always when we're trying to detect where bedrock is using MASW, we try to use some other method that's complementary to MASW, like HRV in this case, or horizontal vertical spectral ratio. We did do the model parameterizations based on the borings, and then we generally take the median of the top 1,000 VS profiles, and that generally produces a more median result, or more muted, instead of taking what is the best model in that case, because there's still a lot of uncertainty involved in it. But we take that 1D VS profile, and you can put them on a 2D line and create a pseudo 2D profile. So it's not a true 2D profile like electrical resistivity tomography or P-wave refraction, but it does provide a okay estimate of what 2D profile or 2D ground surface looks like in this case. So we also use P-wave refraction. So we use the same MASW data, which just requires a faster sampling rate than traditional MASW and shots within the array. General reciprocal method and critical distance methods, which are going to be talked about in the next session, and then seismic tomography or things that we used. The data quality wasn't particularly great in this case, just because there was a lot of traffic noise in for this particular site. Used primarily to determine the depth of saturated materials. So as I said before, the shale rock and the propagation velocity, P-wave velocity of water were very similar at this site. So it was very difficult to pick up where rock was, but we could pick up where saturated layers were below the surface. And this is going to be complementary to the electrical resistivity tomography in this case. And collection of the P-wave refraction data required minimal additional effort in the field and could be analyzed whenever we wanted to for particular arrays. We didn't have to analyze all of it. So that was an advantage of doing that in this particular case. And then electrical resistivity tomography. You've already kind of heard a lot of the background. Mike did a great job kind of explaining the basics of ERT testing, or some people call it ERI. There's just differences between those. So we used a Super Sting R8 system with 56 electrodes spacing somewhere between 1.5 to 2 meters. Academics like to work in meters, so I'm sorry for you guys that are meter illiterate, but that's okay. We did use a combined dipole and strong gradient arrays. This is one that is recommended by Advanced Geosciences, who makes the equipment. That's kind of their common array that they tell people to use in those cases. And then we used Earth Imager 2D to invert the apparent resistivity. Primarily, this was to identify water and saturated layers in the slope, to be able to see those saturated layers, see where water was going below the surface, and with an idea of, okay, can we drain this water out of the slope and be able to increase our shear strength by getting that water out of the slope. So that was the main ideas with this method. And then horizontal to vertical spectral ratio, or HRV. So it uses a resonant frequency of soil to estimate the depth, the stiffness boundaries, or bedrock at this particular site. So it doesn't have to be bedrock, but it has to be some impedance contrast that exists in the subsurface. So this is what creates a peak in the HRV domain. So kind of see down here, we form a peak, and it's due to the resonance or amplification of the horizontal component of the Rayleigh wave, or some people consider it an SH wave amplification. You essentially don't get any amplification on the vertical component, and you get this peak that forms around the resonance. So how we collect this data is just with a single 3-component sensor. We used a broadband sensor. You don't have to use those in those cases. There's much cheaper sensors out there, but we have those available to us. We record these micro tremors somewhere between 15 and 20 minutes at each location, and data was processed according to Seismic guidelines, and we used a MATLAB, frequency domain rejection algorithm that helps us kind of refine the peaks in these cases. But this is primarily used to map bedrock across the site, so we don't have to set up 2D arrays with this. We can have single sensors that move along the site. If you have multiple sensors, you can do multiple measurements at once. You can start to get a much broader view of what the bedrock looks like across the site, rather than a lot of 2D lines in these particular cases. All right, so let's get into where we did all the testing along the slope. So if you remember, this is where all the borings were located. So a lot up here at the top of the slope, and then some down here and on a road that was pushed into the site along kind of the middle of the slope. So we did 5 MASW lines along, mostly horizontal to the slope, and then we ran one down vertically in the slope, and then we collect a lot of HRV data along these different lines in these particular cases. And this was kind of phase 1, or the initial testing. We went back and analyzed this data, and then kind of planned our secondary investigation, which included 8 ERT lines. So ERT lines that kind of matched a lot of our MASW lines, but then some additional ones kind of down here at the bottom, and then a lot of extra HRV and a dense pattern down here at the bottom of the slope. And that's because we found some interesting anomalies down at the bottom of the slope that we wanted to be able to image a little bit better in this case. So let's look at the results. So we're going to start up here at the top and kind of go through each one of these as far as, how they contribute to the overall understanding. So essentially up here at the top of the slope, bedrock is somewhat consistent. It drops a little bit as we go from the left of your screen to the right of the screen, but generally consistent bedrock depth at the site. And we have a general shear wave velocity of the soil, which is relatively stiff soil over this relatively soft bedrock in this case. So nothing really interesting that came from this particular survey. The same thing on the one next to the shoulder, so right next to the guardrail, we essentially see similar bedrock depths across the site, this particular case. So nothing just particularly interesting. And then even in the mid-slope, essentially similar results. And then once we get down to the boring line along the second section down here at the bottom, we see that, again, we're very consistent with the borings. We're showing consistent behavior. Things match up very well. And that was kind of the story until we went to this vertical line running down the slope. And when we started looking at the vertical line running down the slope, things kind of changed a little bit as far as our interpretation. That we see this general consistent bedrock elevation running down the slope until we get to, about 175 feet along the survey line. We start to see this bowl that comes up and this increase in bedrock elevation along the bottom of the slope. And this is just below where this boring occurred. So that was of interest to us in terms of what is this causing to the slope? Because this was unknown during the initial investigation. So this is why we targeted it with our secondary phase, kind of the bottom of that slope, how it contributes. So HRV results. So again, in phase 2, we increased the number of measurements we made out in this section to identify where are we seeing changes in the bedrock in this case. So if we look at the F0, so these are the fundamental frequencies or the peaks in that HRV domain, they are fairly consistent up towards the top of the slope. However, near the bottom of the slope, they start changing pretty significantly, and you can see it along some of the lines. They change from 6.3 hertz to 10 hertz in those cases, 11 hertz, 12 hertz. So that can be a significant indicator that you're getting major changes in the elevation to that bedrock. And although the shear wave velocity does play a little bit of a role in that, if you get major changes in the shear wave velocity, but we're kind of assuming that we have similar conditions across the site in this particular case. So if we use that information to create a soil thickness map, so what does the soil thickness across the site look like? And essentially up here towards the top of the slope, we get very consistent numbers, somewhere between 35 and 40 feet is generally what we're seeing. And then below where the line starts, or the line of borings down at the bottom of the slope, is where things really start to change significantly. We start to see these areas of shallower bedrock where we're pinnacling up essentially, and areas of lower bedrock or deeper bedrock along the bottom of the slope. So everything gets interesting kind of at the toe of the slope in this particular case. And if we take a surface elevation map of the area that we developed using LiDAR and surveying, we can subtract those two and we can get a bedrock elevation map. Or what does bedrock look like in a topographic map? And in this map, we can see some major changes in this particular case. And if we put on top of those what is happening in the site, so we had a number of springs that we observed on the site, and then an old scarp failure from the slide, we see that those match up very well with some of the features we're seeing down at the bottom. So we see some of the flow paths through here and could be contributing to the springs. We see some of the areas up here that could be contributing to why we are seeing springs in these particular locations. So we're starting to kind of piece this together, and now the 3D picture of this, we can see that all across the site where we're seeing these kind of pinnacles and these bowls in the bedrock where it comes back out. So these are all interesting features to us that contribute to the slope stability in this particular case. So now let's look at what does the ERT results look like. So again, we'll start up here at the top of the slope. In this particular case, we see this conductive layer in the slope, but if we plot on top of it the bedrock elevation from our MASW and HBSR, we see that we really can't pick up the depth of the bedrock at this particular line very well. So the shale bedrock and the overlying clay have very similar risitivities. We're having a really difficult time picking those up. We assume this is fill in here from when the road was built, but we're not particularly sure in this case. We go on the other side, we do have this guardrail here that likely contributes to it, but in this case, we're matching up pretty well with the saturation line. So from our P-wave refraction, we can see that this is kind of where our saturation exists, or saturation line. So where all the water is occurring in the slope. And again, we weren't able to really pick up where bedrock was in this particular case. We can't see it because of the similarities between the resitivity of the shale and the resitivity of the overlying clay soil. And for our line here in the middle, we're really not sure what's going on, that this may be a contribution of the anchor blocks and the anchors that were installed in the slope and are covered up now. But we see this very highly resistive layer. It may be some of the fill that they brought in the particular case in order to cover up these anchors. We do see some surface water. We do see a saturated line in this case from P-wave refraction. So we are able to see a saturation here, but we can't really see it with the ERT data in this particular case. And if we go along the line here at the bottom, we see kind of the same section. We're seeing some saturated layers. We see P-wave refraction that matches up very well with the water table depth from one of the borings that was left over from one of the inclinometers. So everything's matching up very well as far as the depth. We get a little bit more accurate in terms of the bedrock elevation, this particular line. If we move down the slope, so this is off to one side of the slope, we start to see these areas again at the bottom of the slope that are very saturated, and these areas that are highly resistive up towards the top. And this likely matches up very well with the area that was cleared to put in the anchors in this particular case and fill that was brought in. If we go to the same line where we have the MASW in this case, we do see this same bowl feature. So in this case, ERT does a very good job of picking up where the bedrock is at the bottom of the slope. We've got this very saturated bowl down at the bottom, which we believe is trapping a lot of the water at the bottom of the slope. We get these features that are impeding the flow of water. That's not letting water daylight out from the slope and slowing us down in those cases. Making it difficult for us to, get the water out of the slope, for the water to move away from these areas. And then if we go over here to the bottom line, we're seeing kind of the same features, not as much in terms of saturated areas, but still these highly conductive areas. And then at the bottom of the slope, we're seeing this all highly saturated area. And again, we pick up the bedrock depth okay at the bottom, but we do have some differences here along one end of the line in this particular case. So if we look at all this together, we see the springs that kind of show up here at the bottom. Again, we see them up here at the top, and all this area is highly saturated in this case. So we're trapping water kind of down here at the bottom, which we think is contributing a lot to this slope failure. Is all the trapping of the water down at the bottom of the slope and weakening that soil material that's trying to buttress the major portion of the slope up here at the top. So kind of the current fix now, this has went along a little bit further now. They're actually out there constructing the current fix to it. So the current fix includes an anchored soldier pile wall. So we've got anchored drilled shafts, so drill shafts that are socketed into the shale, and then have an anchor that come off and bond into the area. And this is in addition to the current anchors that are there. And then some soil nails are being installed in order to stiffen up the section underneath the road and right next to the road in this case. So in terms of the benefits of the case history, so this is some comments from Paul Tinsley with RDOT about the geophysical methods and kind of where they used them most in this particular project to come up with the repair that they did. So, one, the geophysical methods allowed a greater accuracy for the planned length of the drilled shafts and the soil nail elements. So instead of making more guesses in between the borings, like Mike said, we are providing greater accuracy over the larger area so that those lengths can be planned and there's not as many changes in the field. The geophysical methods allow the creation of a more accurate model to reduce the risk that something will be found mid-construction that will invalidate the model or design. So that's a big thing in geotechnical risk, something that A-GaME is really getting into, is how do we mitigate a lot of the risk that come up. Not all projects will we find or observe things that will change the design, but we mitigate a lot of the risk even if we don't find particular features. In this particular case, the saturated areas were identified, but they cannot be effectively drained within the right-of-way or utility constraints. So what this does is provide information that prevents money from being wasted on horizontal drains that do not produce for the project. So simply told the designers that we can't drain these areas because we can't daylight out our drains. So we weren't going to gain a lot by adding a lot of drains down at the bottom of the slope in this particular case. And then 4, it allowed planning of the restraining element location and heights to maximize the amount of load that we removed from that highly saturated zone so that we don't have to buttress as much at the bottom of the slope. We don't have to rely on that area as much as what the previous design did in those particular cases. So kind of some final thoughts and takeaways from this. So geophysical methods results can provide an excellent means of exploring a much larger portion of the subsurface and drilling and sampling alone provide a lot better information between these different borings and places that you can't necessarily do borings. And the geophysical results can reveal subsurface issues which would often be difficult to fully visualize using drilling and sampling alone. And not all geophysical methods are good for all issues. So we saw this in this particular project, that you can't just have one tool in your toolbox and be able to do a good job at a lot of sites. That particular ERT was not able to resolve the bedrock depth at most locations across the site, but provided an excellent resolution of where water was in the site, where was it pooling in those particular cases. And Seismic was not able to always resolve the water in the slope. We had issues analyzing a lot of the P-wave refraction data to see where the water table was. We got glimpses of it in different spots, but it fell apart in other sections. And that's only if the water is saturated. You have to get above 99.5% saturation in order to get your P-wave velocity to jump up to a measurable amount above the soil P-wave velocity. And then HVSR or HRV is a very viable method for mapping bedrock depth, which we've utilized for decades in the earthquake engineering application or world, but it's often underestimated or underutilized for transportation applications. And although it's not part of an A-GaME, we still use it a lot. That I know other people have started using it. Hager-Richter was one that used it in the last session that we talked about for A-GaME. And then finally, geophysical methods, whether resistivity or seismic, are powerful tools for transportation projects. So, you know, if they've got particular applications they can use, they're, you know, very applicable to a lot of the problems that we run into for transportation projects. So that's all I've got. I'm happy to answer questions or anything else that we've got or that kind of came in. I didn't see. Let's stop sharing my screen.
Great presentation. Thank you very much, Clint. Yeah, there actually was a comment just saying how interesting your presentation was and wanting to study that presentation a little bit more. Very descriptive on you know what geophysics can do, sort of course study after the fact, and some of the takeaways that Paul came up with, you know, recognizing that when we do actually determine these types of conditions, you know, that's one of the things that's always hard to capture value-wise, is when we do use geophysics to capture this, there's not a problem, but it's when the problems happen is when they really come to, you know, the value side is spotlighted, but that's not what we want. So yeah. Yeah. So it capturing that value and recognizing that up front, that we are going to reduce problems when we don't have problems, and actually identify these things, just like the drainage solution, which would be a knee-jerk reaction for me on any case. You know, put some drains in, it's cheap, but in this case you would know immediately that that is not going to help you. So
yeah,
great.
Well, if you look at, you know, cost and stuff on there, so as part of another paper that we wrote on this particular project, the amount of money that it cost to do the geophysics was, you know, very minor compared to the repair cost. Yep. And you don't have to have very many of these to go wrong to pay for a lot of geophysical testing or a lot of additional testing on these projects.
Yep. Great point. Very good. Well, thank you very much. And we are populating in questions here. I know that Phil had a comment from the previous presentation on self-potential. And if Phil is here and mic'd up, yep, he's Phil, if you want to talk about that comment, because I don't think any of the audience actually saw your comment on self-potential and what developments are there.
Sure. Jeff did a great job, Ben, if you can hear me.
Yep, I can hear you.
And he made the comment, it's difficult to determine where your SP anomaly might be coming from both out of the mining industry because they use it for exploration in that world. But now in the seepage world, there have been some new modeling codes. I helped generate one back in the 90s, but it was in DOS, so not very useful now. But there's some good Windows codes to help determine where that seepage is occurring in depth. We can tell in plan view pretty readily, as Jeff indicated. But depth becomes an important piece for installing drains or anything else like Dr. Wood just spoke about. And then also they're trying to go and quantify the amount of flow. That'll be the next big step for it. A lot of hydraulics will come into that, and hydrology and geology included, but that's where it is headed.
Yeah, great point. And quite honestly, that is a place where geotechs have not done well in the past on just the characterization of groundwater and its effects. And sometimes we assume hydrostatic conditions where life is steady state. And so I think understanding water, obviously effective stress is a huge part of governing the behaviors of our materials. So we can do a better job on that. And I think that is one technique that can help us, as we sort of see the value of what it can provide. So thanks. We are getting some questions. I want to ask Derek. They're coming in a number of places.
Ben?
Yeah, if you would, but I just want to remind people also, there was a question that on presentations and on the video, is this going to be available? We are going to have these videos available. They're being archived. The issue is that with any bureaucracy, we have our own problems with trying to figure out how to get these posted within the policies that we have with FHWA. So we have to go through a process, and that is in the works. We will have these linked at some point, hopefully sooner than later. But yes, we will have these archived. And Clint, you said you've got a couple queued. Go ahead.
Yeah, we've got a couple of methods. So one came in, did the DOT contract this geophysical work, or was it this through a collaborative agreement with the university? So this was through a research project. So almost all the state DOTs have research arms or divisions that have research projects. And this was a research project that happened to align very well with the start of the A-GaME and work out really well for RDOT in terms of having the university come on and do some of these testing for some of these active projects that they're particularly working on. So the first part of the project was really focused on which geophysical methods work best for particular geology and problems that RDOT has. And then this later phase is all about validation and using these on real projects to prove their worth. So that's kind of how it all got started. In the presenter's opinion, if a DOT wanted to combine methods such as MASW and ERT on the same project, would it be better to use two different consultants, one for each method, or hire one consultant to do both? It just kind of depends on what it is. I'd say stick with one person. That, when we started this project, there was some pushback by some of the DOT folks that, because we used borings to help inform our models when we were doing our MASW and resistivity. And I was like, well, these methods are very proven. We're not trying to prove these methods work. They work. And all we're doing is improving our interpretation of what's there. And I would say that's true of what you're going to get by hiring the same person, is that these are often complementary methods that you want them to work together to provide a better solution. You don't necessarily want to try to pit two people against each other, and because they're using two different methods, you may be able to resolve whatever you're looking for perfectly using a seismic method and not with the resistivity, and that may not be a function of who's doing the testing. I
completely agree with that. We are trying to characterize the site conditions, and that is the objective. And so one element is making sure that who you're working with and contracting with, is well vetted, knows what they're doing. And, we've got quite a few people on the line here that are all of them are good geophysicists that, that's the services that they're providing. So it's not, proving a technology, it's solving problems, and, if them working together, or, that's the goal. So.
Yeah. Well, I've seen like critical reviews before are good
Right.
methods to go about. And certainly not on every project. It gets too expensive, but that's a way to go through if you're interested in getting other people's opinion of the data
Right.
that was collected on the project. So
yeah, and interpretation, that's the other part. We're a lot of the people online here, I'm sure, are just like me, geotechnical engineers. We're not geophysicists, and having our partners, geophysicists, helping us understand those conditions, interpreting those conditions, is, that's not our wheelhouse. So that communication needs to, and we need a certain level of understanding with these methods, which is exactly why we're presenting this these webinars and continuing that on to workshops as well.
So we got one more that came in. So where can you find the paper regarding the geophysical methods and cost savings? So this is a TRB paper that Ben's actually a co-author on. That's going to be, I think it's the conference is the 26th of January, and it should be available online sometime after that.
Should be in TRR. I think it is going to be published.
Hopefully. Hopefully. It's still in the phase.
It's still in the phase. Okay.
Yep. So.
Very good.
So in Florida, we often asked to estimate total grout volume required when compaction grouting is selected as a stabilization remediation repair method for typically relatively small sinkhole features that show up beneath or close to existing roadways, typically only SPT available. What would be the most appropriate geophysical method to estimate total compaction grout volume? Seems like a little difficult. This is a difficult exercise. It would kind of depend on where the contrast is. I've seen both seismic methods like P-wave refraction work well in those cases and seeing voids, but also ERT if there's a good separation between the conductivity and resistivity of the particular materials that make that up. So, sometimes you just got to try things and see what works and for the particular geology. But maybe one of the other guys has a little bit more experience in Florida or doing karst mapping if they want to chime in.
I would also suggest, something like ground penetrating radar if the soil types are right. Florida may not be the best application, but in many places in the rest of the country, GPR, especially for something like volume calculations, it might have a bit better resolution and provide more information for trying to estimate volumes.
Very good. Thank you, Jeff.
Yep.
And then we've got Chris that asks, was there any change detection drone, so LiDAR or photogrammetry prior to choosing the survey locations? If not, do you think pinning down locations of those locations would be worthwhile? Well, in this particular case, we didn't have the ability right then. We were actually working on another project as part of this research project where we're going to use a LiDAR mounted drone to try to see changes in the slope. And in that particular case, the slope failure is much, much larger. So over a much larger, broader area. So we wanted to pin down kind of where we're going to do the testing, but that is an option if you don't understand kind of where the movement was occurring in those cases. So in this case, we saw enough cracks and other things that we felt confident we knew where the movement was occurring in that for this particular project.
Very good. I can tell you are a pro at this platform and answering questions at the same time, and I can't read.
Oh, I do this teaching all the time. I do it mid talking when I teach. So you stop and read questions.
You are a pro.
Yeah. And then we got one more. Hello, everyone. Is there any differences between data processing software programs in terms of results? So what we've shown in recent deals is yes, there are. Now, for For MASW, there are differences in the software, both in terms of the dispersion processing, so which method it uses, whether it's phase shift, whether it's Howley or FK. They can produce a little bit different results. At normally dispersive at what we consider like easy sites, so soil sites with deep bedrock, they pretty much all produce the same results. Now the inversion is a little bit more difficult and tricky in terms of the differences you can get in the results. So the resulting shear wave velocity, there is a lot of uncertainty that's involved in that. So there is differences in the particular software you use. And, you know, some people have multiple software packages that they have on hand, and they can try different ones for particular applications because some have advantages over others, depending on what they do. Like I said, there's only a few out there that do like a joint inversion like we were doing. Geopsy is actually a free software package, although with free becomes more difficult to use. You know, it's not as user friendly in that case because it is free. As far as the ERT software, there's quite a few out there. I don't know much about different ones. I don't know if Mike could chime in about which one he prefers as far as ERT processing software, self-potential or IP.
Yeah, Mike, you have any comments on that?
For resistivity processing, we typically stick with the Earth Imager software provided by AGI. They're the manufacturer of the equipment. I know there are other programs. The Res 2D INV is a common one out there, not as user-friendly in just my experience. As far as SP processing, we tend to shy away from some of the processing programs. I know Phil mentioned that there are new programs in the works, but simply leveling and contouring the data is showing the surface location of the flow. For most purposes, for a lot of our clients, that's what they're after, is just where is the flow located. So we don't even really get into processing software. I know there are software packages out there, but not that we've used them.
Gotcha. Now, Clint, you actually had mentioned an array type that I had not heard of before, and it was something gradient.
A strong gradient. So
yeah, strong gradient.
Yeah, so that's something so you don't use necessarily strong gradient alone. You use it as a combined survey with dipole-dipole. And this is something that AGI recommends that you use. It just improves some of your resolution on different parts of your model. And it generally takes, 2 or 3, 4 minutes longer than what a traditional dipole-dipole survey takes. So it's minimal extra field time, and it improves your resolution in a few different places in the model. So
okay, yeah, and I know that they have. I think in a lot of our applications, dipole-dipole tends to be a well used in providing the resolution that we're looking for, and I think the Werner, when you're getting into noisier environments, that may be the only type that you can use. So, that's good to know. And Derek or anyone else, I don't know. Well, Crystal did ask about a research report and if that was posted.
So we don't have it posted yet because we haven't finished the research project. It's turned into, the 2 years turned into a 3 year, 3 years turned into a 4 year. And we just keep kind of doing things and finding interesting things to do, geophysics and interesting projects and things that we need to validate on the back end of some of these things. So they wanted a little bit more validation about, what was the accuracy of some of these and how good did we do in particular cases. So we're kind of slowly figuring some of those out as some of the projects get constructed. So that's some of the slowdown, is that, some of them are in the construction phase right now. So hopefully that'll come out at some point, in the near future, but it's probably at least a year or more off. We do have some papers that are currently in Geo Congress as far as conference papers, but we also have some journal articles that are just getting into publication right now or in review. So if you want to send me an email, I'm happy to send you whatever we got.
Very good. Thank you, Clint. And Derek, are we missing, or we got all the the questions answered. In the meantime, if any of the panelists have some thoughts that they want to share, we've got just a few more minutes in this this first session here. I did see something.
Oh yeah, Derek asked about plugging the next webinar for sure.
Yep. So, you know, of course we have a 2-session webinar today. This was session 5A. We have 5B coming up at 3 o'clock. So just in an hour, where we will be focusing on the fundamentals of seismic techniques. We do also have CPT webinar scheduled for next week with MWD followed after that. And of course, we've been issuing these announcements a week ahead of time to keep the confusion down a little bit on what webinars are coming up. So just in an hour here, we will have the seismic webinar, and look toward seeing an announcement on the CPT webinar 6 coming up after these webinar 5 here. So if there are no other questions or no other comments from our panelists, we will give you 2 extra minutes before the next section. And it does not appear that we've got any coming in. So thank you so much, all of the presenters. Thank you, Clint. Thank you, Mike. And we've got a great lineup for you here in an hour. And we will see you then. Thank you very much. Take care. Welcome, everyone, to the part B of webinar 5 on seismic methods. Hope you enjoyed the last session. This one, obviously, we're going to be focusing on the fundamentals of seismic methods and sort of a continuation on the case histories, recognizing that multiple methods do provide a better picture. So similar to the last session, we'll probably see multiple methods being used during the case histories, and we will have time to ask questions and field questions at the end of that presentation. So I am going to stop sharing here and let Phil get his presentation loaded here. And as I do that, we do have a number of presenters that you saw there. Phil's going to kick us off here. Phil also joined us during one of the earlier webinars. Phil has a master's degree in geophysics and with an emphasis in geotechnical engineering, has been instrumental in our A-GaME deployment and has over 35 years experience in these methods. Since the late 90s, Phil's been helping with FHWA initiatives and training areas in a number of different aspects and with TRB as well. And he's going to lead us off today with the basics and theory of seismic methods. So Phil, take it away.
Thank you, Ben. I appreciate being part of this EDC 5 webinar series. I appreciated the earlier one done by Jeff, Mike, and Dr. Wood. It was all real good. And we'll kick into the seismic methods here, which does come out of the publication that was done, finished back in 2003, a number of really good chapters on it. But what a few folks don't know is that the back half of this manual is actually a collaborative effect and effort with the Corps of Engineers. And that comes from their EM manual 1110-1. And that has all of the methods for exploration and environmental and engineering geophysics in the physics of it. And so I'm not going to spend a lot of time on the physics. I want to share today the idea of why does seismic work and how we're going to put that to use in the case histories that will be shared to you by CalTrans. The basic information is going to be that we can provide information to design staff on the mechanical properties of those materials that we're trying to characterize with A-GaME methods. And that revolves around compressibility, stiffness, density, the things that we will get out of seismic. You won't hear me mention lithology. That comes out of some of the methods that were shared earlier this morning. But all of our geophysical methods, there has to be a contrast in property. And if there is a contrast, that's where it will work well. So today, when I have about 25 minutes to share with you, that comes from a 179 slide deck from a training seminar that was put on by Central Federal Lands, and Ben Rivers has that if you'd like. These are just a culled down set of slides from that. So the seismic refraction method does have an ASTM standard, as do many geophysical methods now. I believe that's overlooked. They aren't standards in the way an Adberg limit or something like that. They're guides. I wouldn't want anybody telling me all my geophones need to be spaced at 10 feet, but at least you can have your consultants or anybody else you're working with work under these guidelines and make sure they're doing it. Always understand that geophysics and seismic is no different. They're indirect measurements. And so it's not like taking those physical samples out of that split spoon or a piece of core and crush it into the rock. We don't get to do that. We get to make our measurements and infer the results. In the seismic world, there's really only two types of waves. They break down to body waves that travel through the materials of the earth and surface waves that travel along the surface of the earth. And I've been fortunate to gather up a few easy animations that I hope will work on this Zoom setup that we're in. So this is the body wave of the compression wave, called the primary wave, the P wave, VP. You'll see it referred to a lot, but it's about the compressibility of the materials as the wave compresses and rarefies through the earth. The shear wave, called a secondary wave or the S wave or VS, its particle motion is transverse to the direction of the wave. And it can traverse, as it's shown here, in the vertical direction or even in the horizontal, SV or SH as they're called, shear vertical or shear horizontal. Now this one is a fun one. If you look at the blue dots for very long, you'll be a little dizzy, but this is the surface waves and the particle motion of the surface wave, in particular the Rayleigh wave, which was identified back in the late 1800s. It's the ground whirl. It's a surface wave that's felt by earthquakes or even when you hit the hammer or anything else. And its particle motion is elliptic and retrograde. If you learned anything, that's a fun term in particular to its direction of propagation. So body waves travel at the speed that's independent of their frequency. That's an important piece. And surface waves, they're dispersive. And what that means is as they travel through the earth, their speed is dependent on the frequency of that wave. So very quickly in seismic, we start to have to analyze our data different in the sense that we're either going to analyze it in terms of time, if you're talking P and S waves in the body wave world, or S waves and Rayleigh waves and Love waves in the way of surface waves. So understanding that, and you'll see today in the presentation, I put a graphic at the bottom of the screen just so that visually you can see what a high frequency might be or a low frequency might be, just as those waves look on the screen. The real good part about seismic and why I've always used it, my master's and everything was in this, was that the fundamentals of it are based on geotechnical material properties, the low strain elastic modulus. And all of the waves that we measure can actually be associated with these types of modulus. A bulk modulus from the P waves and the compressibility, the shear modulus, or the stiffness and rigidity of those. And then the Poisson ratio, which is the ratio of those axial and radial strains. So in general form, we can work with modulus, and we should be thinking and producing results in modulus, and I'll circle back to that all the way at the end. So real quick, couple slides on the field setup. Many of you might have seen it. Cabled systems on the upper left, and a laptop, and a seismograph about the size of a big lunch pail, and a battery, 12-volt battery will do. Geophones, you have to understand your geophone in the sense of motion. We have vertical geophones, we have horizontal geophones, and they're not all the same in their response. So you can't just grab a handful of geophones and go. You want to think about it before getting there. And then some of the updates are that they're wireless systems shown on the right. It doesn't look real useful here when they're just very close together and the wire coming out of them just goes to the geophone itself. But this is an example on the Mount Lemmon Highway up out of Tucson where you can't see it, but on the slope above those trucks is about 150 wireless geophones. And right down below Clint is a bunch of them just below the MSE wall and then several right along the guardrail there. So it'll really come handy in future uses in transportation, not having those cables run across the road for both hazard and equipment use. In terms of equipment for impacting the ground, the most common is the sledgehammer and having a person that wants to swing it all day or switching off. But there's also vibratory systems. And the good part about those vibratory systems or impulsive is that they generate all of the waves. The P wave, the S wave, and the surface waves are all in the field records. So picking the right source is really dependent on some of your objectives, some of your sites. Vibratory is typically used in noisy environments like along I-80 over in Ohio on the right. But think of this slide as you just threw a pond into the rock. Excuse me, you just threw the rock into the pond. And those waves all go out in an entire hemispherical kind of way in the water and then in a circular way on the surface. Well, that's what's happening when we spank the ground with any kind of source. What we do though is put receivers on the ground, and so we see it in plane or plan view fashion beneath those receivers. I've already mentioned that P waves are related to bulk and shear waves related to shear modulus, so it's not impacted by the pore fluids. That'll be important later when we start thinking about how to measure things in saturated soil conditions. But in essence, the P's are the fastest, S are next, and the surface waves. And where that comes into play is if I try to help deconstruct just a shot record. This is what we acquire when we hit the ground, in this case, just 24 channels. You can have many, many, many channels involved. We do 120 quite often. And the goal here is just that one of these traces represents one wiggle from one received geophone after hitting the ground. But what we're looking for are things in these waveforms and not forgetting that there's an air wave that travels from hitting the ground. We know the speed of that. It's about 1,100 feet per second. Mariners know the number better in water, but the goal being that we can extract some of that information now by breaking this down and saying our full wave formed a set of data on the left is a shot record. The first arrivals are the refracted energy. The hyperbolic events are the reflected energy, which unfortunately I won't have time to cover today. And then the dispersive waves are on the right. That's the surface wave energy. But they're all in that shot record. And in the field, I'm looking for one particular type of that waveform. If I'm doing a reflection job or I'm doing a refraction, first arrivals, I got to make sure I'm seeing those, sites not too noisy. So all of those are in the field records. You just have to know what you're looking for when you start collecting the data. The goal of the data is to have those sensors and receivers and sources put out on the ground. But if there isn't a contrast, as I mentioned earlier, in the case of this schematic, V1 and V2, two velocities for two different formations, you're going to have a refraction, and that refraction is governed by Snell's law that I'll show in a minute. But if we don't have that contrast, in the case of this slide here, it's showing you that the soft sands and clays and landfill materials compared to the limestones and granites are really big changes in the P wave velocity. Thank goodness, because seismic wouldn't work if there wasn't that contrast to define interfaces and layers. Actually, that last slide had a misprint in it. Generalized S wave velocities up top, that's generalized P wave velocities. I'm sorry about that. We can also use the same field setup and put out those horizontal receivers and strike a plank on the ground in two different directions and get the polarity, as I mentioned earlier, with the wave form and the particle motion of shear waves and directly measure shear waves in a refraction mode. It isn't used a lot anymore. In certain conditions, including topography, we try to utilize it. And this is the graph for the shear waves. Showing the difference in velocities from, again, the same sort of materials on the left that are very slow, and then the higher velocities on the right. You might notice, though, that there is no velocity for water because shear can't be transmitted through water, and that's a good thing if you think of a tsunami wave, what it might be like if it could. So what are the applications of refraction? The probably biggest one is depth to bedrock and competency of that rock, rippability. I know that CalTrans is going to show applications of those. and our soil variability, compressibility, and the stiffness of it that we can get out of it. Soil saturation, earlier Dr. Wood showed an example where he was trying to get that out of his seismic data, and often we can in the right soil types. Or rock mass characterization if all you have is a hard rock site. But by getting that lateral and vertical distribution of PNS waves, that's the real key of what these are showing you. So I'm going to stick with the wiggles for one more slide, in the sense that on the left, you've got the green arrivals that are defining and coming in at a slope, and one over that slope is the velocity of that surface. Time over distance. We turn that around and we get speed. So the goal here being, we define these layers, we define these arrivals. I've just shown them in colors. And then we use Snell's law in order to come up with what will be the refracted index, the refraction layer, and start calculating the depths to these layers. Usually the bottom layer, in this case, just shown as a third layer, is the least well constrained. And I know that Bill will talk about some of that as to why when you get into the modeling process itself. Now we can get completely away from the wiggles. We don't need to see them anymore. This is an example from a friend of mine, Mike, at the USGS, where he has about 18 shots across this line, and he's got the pick of the first leg, V1, the second leg, V2, and the third leg, V3. And yes, that is the term we use for it, is legs. And you go through all of this picking and you create this travel time curve. That now becomes the input to start looking at analysis when we want to start saying, I've got dipping bedrock, or I've got sloping one form or another, even if it isn't bedrock, changes in that soil properties. And using reciprocal and intercept times, which are on the axes of these, the time that it intercepts zero or the far distance of the line, that's what allows us to tell us what might be up dip or down dip when we actually have the same velocity of V1 and the same velocity of V2, meaning 2 units, but they aren't at equal distances from the surface. We can also start telling a lot of information if the surface topography is different, or if the topography and a lot of relief on that bedrock, not just dipping. And so this analysis doesn't have to assume flat layers and lateral changes. It assesses lateral changes. So there's really only 6 steps that I've walked you through here very quickly. We acquire the data, meaning we hit the ground, get the wiggles, we pick those wiggles and get the times from it. We assign those slopes, the V1, V2. From those calculated velocities, then we can with the delay and reciprocal times, we can compute depth. And we can compute the depth beneath each geophone with the software code that's out there called Generalized Reciprocal Method, GRM for short. And this is an example just shared with me a day or so ago by Jeff Reed from Hager-Richter, because I thought it was a very good example. He had a bigger slide that also showed 3 layers. This one shows 2. And what you can present is a nice interface between unconsolidated and hard rock, in this case, low velocity over high, 2 layers in a nice simple plot. We don't have to get too complicated about the cross section here of distance and depth. The analysis in this really has a couple of key elements to it. It's based on velocity and depth, as I have explained. The layers need to be uniform laterally as possible, not big changes laterally, and higher velocities with depth. One of the refractions limitations, as I'll share in a minute. And if possible, they extend across at least the length of the spread and a limited number of layers. Most of the codes can't handle more than 4 to 5 layers and get resolution with depth. So I'm going to switch now from what has been more of what I grew up with in the GRM and time intercept and reciprocal methods, but is going to the tomographic modeling that Bill is going to share with you some of the key elements in that and how it works. But if you didn't know, CAT scan stands for computerized axial tomography, and almost everybody has heard of CAT scans, had them, whatever, stuck your head in that hole. And if you'll stick with me for a question of why does it work so well? There's 2 reasons. It works well because they get 360 degrees around your head, your knee, your hip, whatever they're looking for, and that's critical. And it has a really good starting initial model. Other than, say, Bill Owen, my good friend, we all have about the same head. Now, that's just the only joke I get to use today, Bill. But, since we have a good starting model, that works in CAT scan for medical. Well, if we just take from medical and we say what we're going to do is use the same mathematics. I took a class in tomography when it was coming out in 1992, and learned that it's taking every single time through every single pixel, through every single ray angle, and computing the true velocity of just one very small element. And that velocity in the Earth is what we're trying to measure with refraction tomography. So it's using the same mathematics that the medical industry uses, but we don't get 360, and we hardly have good starting models. Maybe a borehole, maybe a CPT, maybe some other direct measurement, test pit or otherwise. That's about what we get to start with. So Mike Powers, again at USGS, shared this example in a publication of saying if we had a starting model that looked like this, just a soft soil layer that's yellow in velocity, an intermediate velocity layer that's kind of a blue and purple, and then a hard rock that's dipping and then flat. What might that look like if we use this tomographic modeling to it? Well, there's a couple different codes. This is one called RayFract that shows pretty good in the center of this model that there's a deeper part of that soft velocity. And there's also some artifacts of higher velocity over to the right. Another code called GeoCT2 shows that deepening of that soft layer is still there in the middle. So we are getting now to the point with our tomograms that we can start saying we don't need that lateral constraints. And some of the things that I showed you just a minute ago that are based on the general reciprocal method. The constant velocity layers laterally isn't necessary anymore. The layers being homogeneous isn't necessary anymore because we have so many more ray density going through pixels, and we can define these layers in a better way. There are limitations, and I believe Bill will explain that. So I just used one example of looking at two travel time curves that I shared earlier about how these work. Just the travel time curves, experienced folks like myself or Jeff or anyone else on this call, Nolan, we look at those and right away we can tell something like on the right is probably a pretty simple 2-3 layer case. We've got some soft soils up top in red, an intermediate layer, and a dipping velocity layer at depth shown as blue. Whereas the left one, those are pretty complicated looking travel times. But they might be due to surface relief or bedrock relief, meaning topography or relief on the bedrock. It ends up in this case, because this is from Florida, flat lying surface, it's relief on the bedrock. The other reason I like sharing these two with you is there is no standard by STM or otherwise in the industry to say red is always hard and blue is always soft, like the left graph. In this case, we're showing you can make it what you would like. I've worked with a number of engineers who say red is bad, make red my bad soil. So you can do that just through the color coding and the colorization and gridding of your solutions. I only have one slide in here. I know that one of the examples from CalTrans is going to show rippability. That comes from P-Wave. In the 1960s, Caterpillar understood that they could sell their product better if they knew how they could rip materials and saying, yes, with a D9 we can do this, or we need a D9 with a ripper tooth, a vibrating ripper tooth. So these are out there. It's a PDF, easy download, but they're based on P-Waves. And I just had that question earlier this week from an engineer. Is it P or S? It is definitely VP. So the refraction limitations, I mentioned that they're limited to line length and the type of source. Kind of get a bigger hammer sometimes will work. In unconsolidated and saturated materials, those pore fluids might be the most compressible piece. And so the P waves cannot be indicative of the soil skeleton. But shear waves aren't going to care about that pore filling fluid. The S waves are a little more difficult to generate in a refraction mode with the planks, but they're a little easier to analyze when you get the polarities. I mentioned how GRM assigns the layers and tomography doesn't do that, but it does have some smoothing and edge effects, as we call them, and even artifacts at those edges. And particularly refraction is difficult in a noisy environment. Those first arrivals that were so clean when I broke down that waveform for you, if you don't have that, it can be difficult to pick those wiggles. But the benefits outweigh that in a big way. That lateral velocity distribution that can be so important, and vertical layering as well. We're able to account for topography in the processing. Now that's in refraction, which you can't do in surface waves yet. It works well in really remote areas. You know, I just can't drill there. I can't put a rig through a wetlands, but you can walk through them. So that's always good. And we get those geomechanical properties. Remember, it's a bulk property measurement. It isn't a sample that tested in the lab. So if we can correlate compression wave with bulk modulus and ripper charts, and we correlate VS with SPT blow counts, I personally did a big analysis on that. The Corps has published papers on blow counts and SPT values in material types, unified soil classification material types.
And then remembering that the modulus we're mapping in this low strain elastic modulus. So moving to surface waves pretty quickly from the perspective of why does it work? There's active and passive surface waves, and I'll refer to REMI in just a little bit. The applications are material strengths in the shear modulus and the stiffness place in the Gmax low strain category. Soil stratigraphy, and I think this helps particularly when you have saturated soils. The layers don't have to increase with depth. You can find those hidden layers in the inversion algorithms that's set up for them. And I've also seen it used on roadways and tarmacs and things where the stiffest layer is right at the surface, and you can see beneath that stiff layer. And the shear wave velocity for the IBC site class VS100, as it's called. So why surface waves? If I share that same 24 channel record I did at the beginning, it's about 80% of the energy from a shot record. For many, many years, most of my early career, we did everything we could to eliminate this ground roll. And so did the oil and gas business. But now we're learning that ground roll can add a lot, particularly to engineering properties. But remember, I said when you go into surface waves, you have to take what is the top seismic trace, a time history, and break that down into the high frequencies and low frequencies. And yes, the high frequencies generally travel in the near surface and shallow layers, and the low frequencies travel greater at depth. You do this through applying a 2D frequency velocity transform. And there's a number of different ones. Dr. Wood shared some of those today. But this basic theory I'm sharing with you that at the high frequencies in this part of the curve, they travel at these lower speeds in phase velocity. And the lower frequency waves travel at the higher speed. That's generally because in the overburden sense, you're going to get more stiffness with depth. We can use this with spectral analysis, where everything started with Dr. Stokey years ago in the late 80s and 90s, using a couple receivers. And then they went to 4 receivers. And we got a sounding at the center point of where these arrays were expanded. Well, it didn't take long for some of you to use 2 or 4. Let's get as many as possible. Well, let's go with what we use in refraction, 24, as I've shared a couple examples, 48, 96. And by doing so, you can come up with what amounts to one SASW-like sounding at the center point of how many geophones you call out. It can be 6, it can be 12, it can be 24. And so we take a shot record and break that down and start saying, now I want to look at this phase shift transform. This is the example I'm sharing here. And look at this fundamental mode and the velocities that are in it. Do a 1D inversion for depth with a layer weighted model to come up with a shear wave velocity sounding, just one depth. The word profile sometimes is overused here. This is a sounding. Well, if we go to that approach where we've got 24 and 48, or we are rolling 24 and moving on down the road, we're getting a lot of these 1D soundings. And we can pick up these low velocities with depth. But eventually what we do is we take those and we grid them up and create a cross-section of shear wave velocity. We are inferring that the shear wave velocity is based on the Rayleigh wave velocity at about 92% of that Rayleigh wave velocity speed is our shear wave speed. So we've constructed this 2-dimensional model to get the appropriate interpolation scheme for top of rock or lateral velocity changes. The nice thing about surface waves is you can collect them almost anywhere. The ambient noise sometimes is your record. This is Sky Harbor and Airport in Phoenix, working right down the sidewalks or down the sidewalks here in Denver for retrofit of that building on the right. And the idea being that that's what you're collecting, is the noise. The record looks like this, a lot different than those timed records. There's no timing to it. You just turn the system on and collect it. If you don't have a lot of energy, you can hit the ground or get any other sources to try and help. From that, you get a one-dimensional sounding, as I mentioned earlier. The REMI stands for refraction microtremor. A friend of mine at my alma mater in Reno, Satish Pillai, produced this as a refraction microtremor method and trademarked that because you use the refraction equipment and you're measuring microtremors, the earth shaking by a bus, plane, train, or any other reason. And from this, we can get this one-dimensional sounding that has a stiffer layer, in this case, a very long or a thick layer of soil down to the bedrock contact just shy of 130 feet. I measured this actual set up by Keystone, and we come up with the International Building Code VS100 if we're working in English units, or the VS30 in metric. And that's the number that goes directly into the IBC for seismic site classification. Very straightforward approach. Takes less than an hour to collect this, 5 minutes for the actual readings, and about 10 minutes maybe to get this velocity transform over into a curve. The surface wave limitations, I mentioned earlier that the relationship of the Rayleigh wave velocity, which is what we're measuring, to the VS, which is what we're inferring, it's not really well constrained. There's a lot of literature, and 92% is generally the rule of thumb. But it is an indirect measurement. It is not the direct measurement of VS, say if you were doing it refraction. Non-unique interpretations, but that's not atypical for most of our geophysical applications. One site borehole really helps constrain that inversion. Clint shared that earlier today in one of his. And you need to understand that frequency domain analysis because there's so many different transforms now. You can collect the data in cross power spectra if you like, or do beam forming or tau p, but the phase shift has been sort of the go by for many years, but the results are coming out to show that there are differences. If you have some experience in that frequency domain analysis, it really helps. I think this is the biggest direct benefit. This is a table directly from the IBC code. It is showing you that if we can map the shear wave velocities and we can start assigning a seismic site classification and get data to 100 feet, we can do that with surface waves with just a 230, 250 foot line on the ground. That's a direct benefit. The other things I like, the easy acquisition, surface waves are 80% of the energy. There is no 3D modeling for it yet, just 1D and 2D. I hope someday that will come. And the low velocity layers beneath a stiff layer at top is a real valuable to us. It's not intrusive, and we get that evaluation of shear modulus and bulk measurements. And I like mostly for surface waves, any kind of impact will work. Vibratory, large, small. With Dr. Stokey, we were lifting the back of cars and dropping them. So it can be just about anything, get that energy in the ground. So this is where I'm going to end, is the P&S approach, as I call it, from the sense of getting 2D refraction tomography for compression waves, 2D MASW for shallow shear wave lateral distributions, and then a 1D passive for getting deeper. The goal here is that we can start combining these measurements by making both measurements while we're acquiring the data, meaning sample rate and record lengths, the things that we understand on our instruments, to get these data combined into one. The last slide I share with you today, this is an MSc wall project that I did for a former friend of all of ours, Kamisa Rami. And we went out and we actually decided what we wanted to deliver to the engineers was not a shear wave velocity or a P wave velocity cross-section. I've yet to see a designer work in that space of velocity. So when we assign generalized layers and we get unit weights, it isn't hard to go to 2D sections that's just in modulus, as long as you understand it's not deformation strains, it's down in the elastic strains. I know that these information can be used in a much better sense. This is where I believe we'll be going much closer in the future than further for seismic measurements. And I believe that's a wrap, Ben. I hope I stayed within some time here to let everybody else get going and show some case histories.
Excellent. Thank you very much, Phil. Great presentation. I will let you turn this over to Bill, and in the process here, I will introduce the CalTrans crew. We've got three presenters led off by Bill Owen, who is a licensed geophysicist with CalTrans and is the chief of the geotechnical geophysicist and geology section there, and has also been part of our A-GaME implementation team. And we've got Will Dalrymple also presenting, licensed geophysicist with the group, and has a history of working in consulting with mine sites and nuclear, chemical plants, environmental worldwide. And his primary focus right now is in seismic, electrical, magnetic, and GPR methods throughout California. And then we have Nolan Lua, who is a geophysicist with CalTrans and has worked in consulting and with the USGS with the Earthquake Information Center, a Marine, served in the Marine Corps, and earned his bachelor's degree at the Colorado School of Mines. So I will turn it over to you, Bill. Thanks.
Great. Thank you, Ben. So I'm going to start off with a introduction of using the optimized tomography models for geotechnical investigations. A lot of the stuff that I'm going to talk about for the introductory material here really applies to the next two presenters as well. Essentially, what we're doing is we're stepping, as Phil showed you, you had the introductory material that showed you what tomography is and how it works. I'll go into a little more detail about that, and I'll talk a little bit more about applying constraints to the tomographic inversions to try to come up with realistic geologic models. And that theme will occur throughout this presentation. You'll see it in Will's talk, and we'll finally close out with Nolan's talk as well. So essentially, by using tomographic inversion techniques, we are able to develop two-dimensional models of complex velocity distributions using just first arrival times and array geometries for input. Now, combining these models to observed borehole geology or other geologic information available on the site allows us to assess data gaps and to develop satisfactory geologic interpretations of the velocity structures with a high degree of constraint. So I'll hit on three basic discussions here. One will be an overview of modeling techniques. I'm talking about uniqueness and optimization in modeling. I'll talk about some of the advantages we've achieved using novel seismic arrays for site investigations, and I'll present results from two Northern California examples. So before we dive into modeling, it's important to understand the difference between direct solutions and modeling. Now, direct solutions are solutions that are directly calculated from known mathematical relationships. They tend to be reasonably straightforward and can often be performed on a hand calculator. They provide a unique solution defined as having one and only one solution for a given set of conditions. And they are usually simple answers. That is something like depth of water or average seismic velocity, resistivity, something like that. Modeling, by contrast, uses more complex mathematical algorithms, and it requires computer processing. Modeling is required when conditions violate assumptions for direct solutions. A model is still a simplified representation of physical conditions, but with fewer or different assumptions. Now, two different flavors of modeling exist. Forward modeling is used to determine the effects of a known model. So in other words, if you know the distribution of your material properties, you can calculate using a forward model the effects of that distribution on your criteria or your phenomenon that you're trying to observe. Inverse solutions, however, are used to determine a model from the effects. So it's almost the reverse of what we do for a forward model. Now, it's important to note that inverse solutions are non-unique. What that means is that just because you have agreement of a model with its observations doesn't prove the accuracy of the model to represent the real world condition. So when we talk about doing inversion, there's essentially two components of inversion that we deal with. One is estimation and one is appraisal. Now, the process of appraisal is known as optimization. So when we deal with appraisal, it's important to note that with all geophysical methods, if all we can see are the effects from a geologic structure, then we cannot deduce the one true causative model for that effect. In actuality, there are an infinite number of possible models that can satisfy the effects that we're observing. And in addition, real data are always noisy, and that noise propagates into the model. And equally problematic is that we as yet have no easily implemented means of evaluating the differences between models within this universe of solutions. So that kind of begs the question, how can we determine the true causative model from a universe of models that can equally represent the effect that we're observing? And the answer is that we essentially can't, at least not easily. What we try to achieve, or what we try to achieve through modeling, is that we try to come close to the actual causative model. In other words, we're trying to get close to reality through modeling, and we get there by applying suitable constraints to our model. Now, fortunately, the Earth readily provides those constraints to us. Not all geophysical models are valid for known geologic conditions. For example, the Earth has finite dimensions. Crustal rocks have a maximum density and a maximum seismic velocity that we can realistically anticipate. We can immediately pare down then our solution universe to those models that are geologically plausible, which can still be a large number, as a matter of fact, and then use additional actual geologic observations from your site of interest to provide additional constraint to the geophysical model. Now, it's an important point before we move on here to understand that inversion without ground truth is a risky proposition. Some knowledge of local conditions and physical properties of the earth materials that you're studying are always required, and judicious use of common sense in the application of your resulting models is also necessary. So when we discuss the optimization process, successful inversion relies on computation and evaluation of multiple models. Now, often thousands of models must be compared to arrive at an acceptable solution. So we use optimization to allow an inversion algorithm, so our tomographic inversion, to compare many different models and converge to an appropriate solution. Now, there are different optimization schemes available, but all follow the same conceptual process. One is you calculate the effects of an initial model and compare those results to the observed data. And the results of that comparison is then used to determine the model's acceptability. Now, that model you can either reject outright with your acceptance test, or you can conditionally accept it. You can modify it and compare it again. So this is where we go through the adjustment loop in the appraisal process here. And then once we get to a point where we have a final acceptance criteria, we can finally accept the model based on whatever criteria we need to select on, either a reduction of a model error below a specified value, exceeding a set number of iterations in the appraisal process, or meeting a specified difference between successive iterations. In any case, once that criteria are met, the final model is accepted and optimization ceases. So there are two types of optimization that we can look at. They're known as local optimization and global optimization. Local optimization schemes converge to a solution close to the initial model. So essentially, if we think about our error distribution within a model universe, if we look at the number of iterations and the average error in our model, the local minima is the one that's closest to our initial model. So the key point to remember here is that a locally optimized routine requires a reasonably accurate initial model. So some form of existing subsurface information is needed to constrain the solution. Global optimization, in contrast, includes some statistical tests that occasionally will reject an acceptable model near the local minimum in favor of one with a higher error. So in this manner, the algorithm is less dependent on the initial model because it can escape local minima to converge to a more robust solution based on evaluation of the entire solution range. And that's what we call the global minimum. Now, there are some advantages to incorporating these global optimization techniques with some novel downhole arrays. Typical seismic refraction surveys, as you saw in the introduction, are limited to sources and receivers at the surface. So beginning in around 2003, we began using globally optimized modeling using surface arrays only. And we rapidly progressed to include downhole sources, downhole hydrophones, and transition zone receivers for borehole and shallow water regimes. Now, this allows us to accommodate site conditions where traditional refraction techniques would not succeed, such as high noise environments and areas of limited access. So use of the global optimization scheme allows us to escape from those local error minima and develop some more mathematically robust models that are relatively insensitive to initial conditions. Again, the only required inputs we use are first arrival times and array geometry. The outputs that we get are the subsurface 2D velocity plots, a seismic ray path distribution to allow us to evaluate quality of the model solution, and a comparison of the observed arrival times versus the modeled arrival times. And finally, the optimization techniques do allow us to tune the models using observed geologic data, either in borehole or at the surface. It's important to point out, though, that once we start doing something like that, we're no longer using a global optimization scheme. We're actually locally optimizing it, and we're allowing the solution to actually converge to a local minima rather to the more larger iterative global minimum. So it's just a little piece of detail that occasionally you need to be aware of. So I'll talk about our first example. There are two types of constraints that I'll talk about in these examples. The first is going to be some a priori constraints, or basically applying some geologic information that you already know about to constrain your model. This example was a seismic refraction survey at Willow Creek and Interstate 80. There were 2 borings drilled at this site, and they indicated that depth to rock was highly variable. In boring number 2, depth to rock was about 10 feet. In boring number 1 over here, closer to the roadway to the southeast, depth to rock was about 70 feet. So now this was a heavily traveled urban freeway with a significant broad spectrum seismic noise, and we had a limited footprint available for the seismic array. You can see that we had heavy traveled, we had traffic ways on either side, and over in this area to the southeast, we had businesses, and again, we were very close to the freeway. So what that ended up meaning was that we really didn't have a lot of a good footprint to work from. So what we ended up doing was we actually used the existing boreholes to set up some deep shots and to see how that would work using these tomographic routines. So this is an error plot of the optimization technique used in this application. Now, the early error peak shows the global optimization algorithm rejecting low error models in favor of those models with a higher global error. These kicks help the process, again, escape from local minima. So in later iterations, we can see the rejection tolerance decreases and the solution converges to a global minimum. In this particular example, almost 53,000 iterations were performed to converge to the final model, and total processing time was approximately 17 minutes on a 1.2 gigahertz processor. And the model was further manually tuned using the geologic information from the geologic ground truth from the test borings, and were used to fine tune that model. And the result that we ended up with using these geologic constraints is presented here. And so what we can see here is that the top of the sandstone varied between, again, as we can see, between basically 10 feet and 70 feet. And the result here tied in very well with the existing information. And in this case, what we can actually see is that there is a zone of weathering in the sandstone up in the top here that wasn't initially indicated in the borehole log. So we ended up confirming through later inspection of the actual cores. The geologic correlation presented here as an overlay. We had a water table in this borehole. We didn't have water table in this borehole, which is very interesting. And you can see we have this high velocity, moderately weathered the fresh sandstone in this area. And most notable is that we see that the sandstone is not at a constant dip. And indeed, what we have here is we have an erosional bank here from channelization of a Pleistocene paleo channel. And at least that's what we believe it is. We don't believe it's fault controlled. So that was a good example of how we can use these borehole information along with these borehole sources to kind of develop these different models. And so we can also present the ray path plot in order to try to find the assessment and evaluate the assessment of data coverage and the quality of the solution in the model. In this particular example, we're not actually presenting the rays themselves. We're presenting a count of the number of rays crossing any given pixel. And we use that to construct an approximate path of seismic rays from sources to receivers. Higher hit counts, that is the number of rays crossing a pixel, correlate to regions of increased model confidence. Blank areas correspond to regions of no model data and represent zones of uncertainty. Now, ray path approximations and hit counts help us to fine tune the geologic interpretations. These ray path deflections or zones of higher hit counts, for example, up in these areas here, give us clues to the presence of refractors that can be important to the interpretation. And finally, The lowermost ray path, in other words, the lowermost ray path that travels from a source to a receiver, gives us a constraint for depth of investigation. And this is unlike intercept time direct solutions that you saw in the previous discussion that don't provide a depth of investigation. And then finally, in this example, we can actually evaluate how the deep borehole shots contributed to the success or failure of this particular survey. So the top of the sandstone and the limits of the original model are overlaid here for comparison. And by eliminating these two shots in the modeling process, what we ended up with is a result that made it obvious that the deep shots were absolutely critical to the success of this investigation. Without those deep shots, especially without the deep shot near borehole 1 at this location, the top of the sandstone and the erosional channel to the southeast would have never been imaged. We would have never seen it. So we would have never realized what was going on in this location. So this was a critical target for our investigation, and this is the only way we could have imaged it was with that one borehole shot. So I'll start and I'll close out with our second example. This is State Route 162 in Mendocino County, California. And here is where we used statistical constraints rather than existing geologic constraints to constrain our model. We're going to focus on this long array right here. This is going directly down slope. This whole area here is an active landslide that's impacting the highway. We have steep slopes, complex geology, including large component blocks within the slide matrix. And so here, using a statistical constraint, this is going to be more applicable in an area where you don't have good existing geologic information on subsurface conditions. Here we did have borehole information, and we used it to evaluate the results of the statistical appraisal. But unlike in the previous example, we actually didn't use that borehole data to fine tune this inversion in order to double check and see how this process might working for future investigations. So this is the final velocity plot that was produced from an average of a number of different models. We first of all used test runs to optimize resolution settings for this model. And then ultimately we ran 7 models using the same cell sizes, but using different maximum depths. And ultimately we rejected 1 model so that we ended up having 6 models that we averaged out for a final output. And this is what we see here. This is essentially an average of every pixel in this model. Essentially, there are about 30,000 pixels in this model. Each one of those represents an individual velocity. And we average those out 6 times to develop an average velocity at each pixel out here. So pretty computationally expensive, but it ended up with the result that we saw here. We can see that we had good correlation with the transverse refraction profiles that we acquired for this survey as well. We had some differences in the borehole logs that we observed. We had good correlation here, moderate correlation here, and weak correlation in this area. The velocity scale that we used is tied into the CalTrans ripping limits. And it's important to point out that this isn't a cookie cutter approach. This appraisal process is going to be dependent on site-specific acceptance criteria, and it will vary from site to site depending upon what your project needs are. And so finally, what we did for this is we developed a tolerance plot based on the perceived quality of the final solution. So what we ended up doing was we calculated the statistical parameters at each common grid cell that we used to derive this, this final model. We developed a standard deviation at each grid cell. We looked at maximum and minimum velocity ranges, and we flagged results at grid cells that exceeded the tolerance criteria. Now, the tolerance criteria applied here are based on presumed construction remedies for the control of the unstable slope. The candidate controls were a soil wall, MSE and soldier pile walls, where presence of competent rock would impact constructability. That's the red areas on this plot. Now, it was important to know what confidence we could place for the rock extents. Now, this type of plot provides an easy visual that outlines where the final model exceeds our tolerance criteria for location of rock. These blank zones represent areas of lower confidence in the model solution. Now, it doesn't necessarily invalidate the model, but it indicates areas where if these are going to be critical areas for design or constructability, we need to go out and do some additional investigation to evaluate the accuracy of the ultimate final model. So in summary, just point out that we use models to represent real world conditions, and optimization allows models to converge to a stable solution, and user-friendly validation processes, as we identified earlier, are still needed to compare multiple solutions. But the use of these globally optimized inversion algorithms with surface and downhole sources and receivers give us greater flexibility in field acquisition and improve constraints to the geophysical model. And with that, I will turn this presentation over to Will Dalrymple, who will continue talking about how we use locally optimized routines for providing data for CalTrans investigations.
Hello, hello. I assume everyone can hear me okay. So my name is Will. I'd like to continue on with Bill and Phil's discussion by focusing on seismic refraction. Since seismic refraction as a geophysical method has already been covered in this session, we're going to focus on applications and processing instead. So we're going to go over why seismic refraction is useful to us at CalTrans, the various ways we process seismic refraction data, and how we determine what processing method we are applying where. Then we're going to go over some case histories of projects here at CalTrans, after which we're going to wrap things up and hand things over to our next speaker, Nolan, who will give a rundown of surface waves. Seismic refraction is an important part of the A-GaME initiative to provide better geotechnical data for design and construction. For transportation projects, we mainly use seismic refraction for subsurface mapping, rippability, and earthwork factors, as well as slope stability. As expected, most of our projects are around highways with focuses on road and curve realignments, lane additions, and repairs, which include culverts and slope failures. For subsurface mapping, we're typically looking for depth to rock, depth to groundwater, areas of possible failure, landslide extents, and other features like faults and paleochannels. Since transportation projects can involve large amounts of earth movement, we also provide rippability estimates. These estimates are based on the seismic velocity of the material, which is closely related to the density of the material and gives construction a guide on what equipment is appropriate and if blasting is required. We can also provide earthwork factors of known materials, which is basically how much the volume of material can change after excavation from shrinking or swelling. Material excavated on site can then be properly accounted for when filling and leveling for other areas or sections on site or at other projects. A vast majority of our seismic refraction projects involve slope design, stability, and repair. With seismic refraction and other methods, such as electrical resistivity imaging, we can determine the depth and extent of landslides and debris flows for remediation and mitigation. We can also determine geotechnical characteristics such as dip and structure, as well as velocity of the subsurface units, which provides data to the design team so they can use the appropriate layback and angle for cut slopes. Overall, seismic refraction can provide useful information for design and construction. However, due to scrutiny on budgeting for all phases of a project, geophysical studies are sometimes skipped to save on costs. This can lead to ballooning costs later in the project from overdesign, redesign, change orders, delays, and replanning. If design teams do not have all the information that can be provided, you can imagine they will need increased factors of safety, such as shallower cut slopes or increased slope layback, which can lead to more material being removed or more right-of-way to be acquired. Most of the actual cost overruns are in the construction phase, though. There they can run into unexpected subsurface conditions that can cause significant issues, such as full crew standby, equipment changes, or redesign. Geophysical studies can be the insurance against these unexpected conditions so that significant costs are not incurred during project execution. Next, let's discuss the various ways we process data, starting with the technique that has been an important part of the geophysical toolkit, the generalized reciprocal method, or more commonly GRM. Briefly, GRM is a layer-based processing technique that uses both forward and reverse shots to determine the critical distance of refraction. To start, the first arrivals are picked and then assigned to different layers as shown in the top section of the graph. The results are then phantomed or matched with forward or reverse base shots to create curves for processing. The results of processing have a velocity assigned to each layer as shown in the middle of the graph, and the modeled depth or elevation of each layer as shown at the bottom of the graph. Data are assigned to discrete layers, and as a result, more gradual changes or structures that do not span the width of the data can be averaged or hidden. So gradual velocity changes such as weathering or transition zones become part of a single uniform layer. This process works best in layer cake geology with well-defined contacts like landslides or other depositional environments. Another much used processing method is seismic refraction tomography. The principles of seismic tomography and global optimization schemes have already been discussed in the previous presentations, so I'd like to focus more on how we process using local optimization routines and how we apply the constraints to the inversion process. As already discussed, inversion routines that use local optimization require more careful selection of the initial model. Two types of starting models can be used: 1D or smooth starting models and layered or defined starting models. 1D models use a single vertical profile of velocities that are extrapolated across the full width of the refraction data. 1D models are less representative of actual geology, but are appropriate for geologic structures that exhibit smoother velocity transitions like thick weathering zones. They may also be used when defined layered models can't be developed. However, because 1D initial models create smoother velocity distributions in the final model, they may not be appropriate for geologic structures that exhibit more abrupt velocity contrast, such as translational landslides over rock. In these cases, this can lead to underestimating interpreted depths of geologic contacts. This is where we try to improve the constraint with well-defined layer-based starting models, which are typically created from GRM processing. If borehole or other geotechnical information is available, we can also add other features such as saturated zones or hidden layers to try to better model these conditions. By using layer-based initial models to constrain the inversion routine, we are trying to provide a more accurate starting model that can be inverted to result in a better representation of the true subsurface conditions. The inversion may still produce a result that exhibits deviations from the initial model, but will also converge to a final result that bears similarities to the starting model. Next up, we're going to look at some actual data that shows when and where we're deciding where we determine what type of initial model to apply when using tomography modeling. Here we have a project in Plumas County, California along Highway 70. We were tasked with determining the velocity structure using several lines for slope stability and rippability to aid in proposed slope adjustments and curve corrections. So let's focus on line SL12, which is on the west side of the rightmost aerial image. Both this line as well as SL15 were located on the road cuts above Highway 70. For SL12, we encountered a complex structure that was problematic for layer-based processing. The travel time curves indicated the presence of one or more structures, such as a fault or an intrusion, that made processing this line using GRM very difficult. So due to the complex structure, we opted for a 1D or smooth starting model to process this data. What we have here is a general flow of how we create the initial 1D starting model. First, as with all refraction processing, the first arrival data are picked and a set of travel time curves is developed. For smooth starting models, we do not assign layers to the curves as we do for layer-based modeling. Next, we select several points of time and distance along a scatter of the curves, trying to achieve a rough fit. We use more velocity breakpoints to better fit the curve as compared to the number of layers that would typically be assigned for layer-based processing. These points would then convert to velocity and elevation, and finally extrapolated to create a smooth starting velocity model like we see at the bottom here. So this is the result of our inversion. For this and the upcoming models, blues indicate slower velocities and reds indicate higher velocities. We use a more conservative ripping scale compared to the often used Caterpillar ripping chart. Our scale is shown in meters per second and is based on in-house CalTrans experience. Notice that the vertical distribution of velocity contours in the final model shows a relatively large spacing, indicating a more gradual velocity gradient. If the velocity structure is actually more abrupt, even though we use a smooth starting model, the velocity contours will still be expected to be spaced closer together and exhibit a higher velocity gradient. As anticipated from initial review of the travel time curves, we can see a distinct structural change at the center of the model. The higher velocities are offset from low elevations on the western side of the model to higher elevations on the eastern side of the model. Since this profile was collected inboard along a road cut adjacent to the highway, we are able to compare our results from the inboard seismic profile to the visible geology on the cut face. Placed on both the model and the picture of the slope is a black dashed line, which shows the approximate interpreted transition in geologic units. Comparing the transition between the finer material at the top and western side of the slope and the coarser rocky material at the bottom of the eastern side of the slope, we are showing very good agreement between the model and what is visible. This transition appears gradational rather than the discrete distinct contact. This type of gradational contact is better imaged by the 1D smooth starting model. Now we're going to look at the seismic line SL15 from the same project. The travel time curve showed a more consistent consistent layered velocity structure, and therefore we were able to use the layer-based GRM method to initially process the data. Again, the first step in processing is to pick the first arrivals of the seismic data, but this time we also assign layers to the curves as shown using different colors in the travel time plot. As discussed previously, GRM processing was applied and the resulting layers were tied to elevations and velocity. We then combined the elevation and velocity information to create a defined layered starting model for tomography processing. Before inversions were run, the starting model was smoothed slightly to add some gradual velocity contrast at the contacts in order to reduce the extreme velocity gradients at the refractors and improve the efficiency of the inversion routine. So here's the result for this example using defined layer-based starting model for the inversion. As you can see, the tomography model strongly reproduces the structure of the layer-based results. Again, this is a local optimization. That result is expected. However, velocities between the GRM and the tomography models show some differences, especially at depth. These differences can be attributed to how the GRM is averaging larger sections of the model into a single velocity layer, whereas the tomography result shows more variation in velocities. So looking at the road cut outboard of the seismic line, we can see several geologic units in the same general structure as imaged in the seismic model. The layer-based methods are following the top of the blockier formation at the bottom of the cut. However, the more fractured rocky material directly above that in the western and middle of the line is imaged in the same layer as a finer grain material at the top and eastern side of the line. Although we can visually differentiate these units, they are not showing up as separate velocity units in the layered model. Also, the more fractured rock material does not fully extend across the width of the line, which is difficult to capture in GRM analysis. But if we look at the tomography model, those sections are imaged as velocity gradations with faster velocity for the fractured rocky material and slower velocity of finer grain material. So even though we are using a layer-based starting model as a constraint, tomography is still able to capture more variation in velocities that layer-based methods may average out. This is why, if conditions allow, we prefer to use the layer-based starting models in tomography. We're able to image more discrete contacts while still allowing for more gradual contacts to be imaged. Now let's look at an example where, even though we can see the exposed surface of the slope, the expectation from what is visible can be different from what is actually hiding beneath the surface. Here is a project in El Dorado County, California, along Highway 50. This area is very active for landslides, which has posed a problem for a particular down drain pipe. We're going to focus on the area that SL1 covers, which is on a slope above Highway 50. Here we have a couple of diagrams created for a seismic refraction survey was conducted. These were created from superficial mapping and no borehole information existed at the time. The first sketch shows a cross-section with an estimated depth of rock and the location of a slumping or slide feature. The second sketch is directly looking at the slope with a down drain pipe visible within the map slump feature. From surface mapping, it is expected that a shelf of granitic rock was supporting a slump of looser landslide material with some blanketing of the shelf closer to road grade. This shelf corresponds with the break and slope seen with the queried dashed green line in the first diagram. We were tasked with mapping the subsurface structure using seismic refraction to determine what was mapped could be confirmed and with measurements. With some ropes, experienced climbers, and traffic control, we collected a line going straight down that slope in hopes of imaging the extents of the slide material and depth of the expected rock. To give an idea of the slide movement for that slope, that down drain pipe in the picture was initially installed straight. As can be seen in the image on the right, the shelf of mapped granitics was based on the exposed rock adjacent to the down drain and debris chute. Due to the obscuring slide material, assumptions had to be made when trying to initially map the geologic structure within the chute. Already in the seismic tomography model, we can see that the rock is not as shallow as initially thought. The layer of granitics mapped near the breakage slope was not imaged at the corresponding portion of the debris chute. A slightly higher velocity is at the bottom of the debris chute, which is probably an accumulation of rockier consolidated slide material at the bottom of the slope. Also, from the variation of the velocities in the upper layers, floating blocks of granitics or more consolidated sections within the slide may exist. So instead of a full unit at shallow depth, the exposed granitics may actually be floating within looser material, or the areas outside the line may be structurally different than at the line. So let's take a look at the model with the preliminary mapping of the slope. Comparing the diagram with the layer-based starting seismic tomography model, we can see the differences in the results with what was initially expected for the slope. As discussed, the expected competent granitic layer is not as shallow as initially thought and has a thicker section of overburden, as well as a likely weathered section at the bottom of the slide. The expected dip direction of the granitics is also different, with the tomography model showing a dip loosely paralleling the slope and the diagram showing a much steeper dip. However, the expectation of a thick section of landslide deposits over the granitics is consistent with what was initially thought for the chute and also corresponds with the landslide scarp that was seen at the top of the slope. The differences in what we were able to gather from the seismic refraction survey as compared to the expected structure shows the value of having geophysical data before the design process. Without the seismic refraction data, the slope may have had a very different mitigation design or a construction phase with costly unexpected subsurface conditions. So finishing things off, the seismic refraction method is a common and much used tool in geophysics. At CalTrans, we use it for subsurface mapping, slope design, repairs, rippability, and to also provide earthwork factors. We use GRM, 1D starting model seismic tomography, and layer-based starting model tomography for processing. In general, it's preferred to use layer-based seismic tomography for our data processing, but 1D SUSE model tomography is also a good second choice for areas of complex structure and gradational seismic velocities. So although valuable data can be gathered from a standalone seismic refraction survey, seismic refraction is best used as part of a whole investigation process that can include other geophysical methods such as electrical and electromagnetic techniques, as well as geophysical logging such as PS suspension logging, optical and acoustic televiewer, and e-logging. Of course, this process also includes geotechnical borehole logging, geologic mapping, and regional geology review. So in short, geophysical investigations are an important part of the site investigation process that should be utilized where feasible for better planning and design. So that ends things with me. So I'm going to hand this off to Nolan Luwe, who is going to go over the surface waves method.
All right. Okay, is that going? Okay, thanks, Will. Hello, everyone. As Will said, my name is Nolan Luwe. I'll be talking about how CalTrans has been using surface wave methods for the determination of VS30, focusing on the multi-channel analysis of surface waves, or MASW. Here's a quick rundown of the topics that I'll be covering in this presentation. First, a very brief overview of the theory governing and applications for surface wave methods. After that, a look at how CalTrans has historically approached the acquisition of VS30. Next, we'll look at the development of guidelines for surface wave acquisition, processing, and interpretation. We'll then examine an example of a recent project in which surface wave methods were utilized. After that, we'll address changes within CalTrans in the use of surface waves for site class characterization. And finally, we'll discuss our ambitions for the method as we move forward. Phil covered most of this, so I'll just do a quick overview of surface waves. Rayleigh waves occur at the ground surface, hence their name, surface waves. These waves are dispersive with depth and frequency dependent. The measurement and analysis of this dispersion can be used to gain insights on the subsurface velocity structure. This velocity structure defines a site class seismic site class, which in turn impacts structure design. Besides site class characterization, surface waves can also be used for quality checking soil improvement, pavement testing, and anomaly detection. Some of the inherent benefits of surface wave testing are that this method is non-invasive and does not require a borehole. This reduces investigation costs that potentially allow for a higher resolution site investigation. These surface wave measurements examine aggregate velocities below the survey length as opposed to an isolated point obtained by borehole investigations. Another benefit is that refraction data are collected simultaneously, potentially providing valuable data such as depth to bedrock, rippability, and depth to groundwater. It is important to note that, as with all geophysical methods, this method is not applicable to every site or scenario. In order for this method to be effective, certain site conditions should exist. Shallow rock sites make surface wave methods difficult, if not impossible, to effectively conduct. Sites with significant topographic variation should also be avoided. Spatial demands of the method require large open areas. And finally, lateral subsurface density contrasts, or 2D velocity structures, cause issues for the surface wave method. An example of this would be a dike or a major undulation of bedrock. As discussed previously, the physical theory and mathematics governing this method are based on a layer cake model in which velocity increases with depth in a planar geometry. And although love wave propagation can be probed for additional information, the geophones we're currently using are vertically oriented, so our process focuses exclusively on Rayleigh waves. Here's a look at the process of surface wave data reduction and interpretation. The seismic shot record on the left contains information about Rayleigh wave dispersion and body wave refraction. This seismic data undergoes a wave field transform followed by Fourier transformation in order to derive the phase velocity as a function of frequency. This phase velocity as a function of frequency seen in the middle image is the data from which a dispersion curve is picked. The picked dispersion curve is then used in the inversion modeling algorithm developed to develop a model of the subsurface velocity sounding from which VS30 is calculated, as seen on the right. It can be seen clearly here that pivotal to the creation of a valid velocity model is the effective acquisition of seismic shot records. So here's a depiction of the field data acquisition process for MASW, or multi-channel analysis of surface waves. We can see in this image the ideal layer cake model. Each hammer image represents a type and location of source energy. The greater the energy source and array length, the greater the potential depth of investigation. Conversely, in order to examine relatively shallow material, it can be beneficial to use smaller energy sources propagated over shorter array distances. We use a wide variety of source types and shot locations in order to very thoroughly examine as many frequency bands of the dispersion curve as possible. This method also provides greater data density than a more standard approach and allows us to select the fundamental mode of the dispersion curve with a higher confidence. We also collect passive surface wave or microtremor array data, which observes lower frequency ambient noise sources such as the ocean or distant traffic in order to image greater depths. This is part of our improved approach to surface waves, yielding higher resolution data with a better idea of the uncertainty contained in our dispersion curve and therefore velocity model. As with all geophysical and geological models, we are providing a model, but it might not be the model. There exist an infinite number of models that provide an equally good fit to the observed data. Many of those models will not be geologically plausible, as can be observed within the image on this slide. One of these models shows significant velocity inversions occurring at depths of 5 to 20 meters in layers too thin to confidently be resolved. This unlikely model provides the same fitness with the measured dispersion data as a more realistic model with velocity increasing with depth. It is therefore very important to provide appropriate constraints to the inversion process such that we produce a reasonable number of acceptable models that realistically approximate actual site conditions. The CalTrans ARS module lists a number of tools or methods for the calculation of VS30. The list seen on this slide provides an effectiveness ranking as historically held by CalTrans. PS suspension data was and remains our gold standard for VS30 calculation. Seismic CPT is also considered a top-tier method for this purpose. Downhole is, for all intents and purposes, the same as seismic CPT and equally effective. And while cross-hole seismic is also effective, it requires 2 dry and stable boreholes, which is an added complexity and cost. Although valuable, CalTrans does not conduct downhole or cross-hole seismic investigations. CalTrans previously utilized REMI, a 1D passive measurement analyzed within the SeisOpt software exclusively for surface wave analysis. Lastly is SPT, CPT correlations. These correlations and their associated uncertainties can sometimes be problematic and should be utilized after exhausting the options above. Due to the growing popularity and common misuse of the surface wave methods, guidelines have been evolving to attempt to create a standardized approach to the collection, analysis, and interpretation of surface wave testing. Because the velocity sounding derived is a non-unique solution, as discussed previously, the variability inherent to the method must be effectively communicated in order to provide defensibility to the calculated results. In 2014, ASTM received a research paper published in the Journal of Testing and Evaluation that provided a case study of surface wave field and laboratory testing. This paper, while providing an excellent overview on the method of surface wave testing, did not provide best practice recommendation or guidelines for the method. Shortly following, SSA held a special session at Caltech in 2015 to discuss and disseminate applications and experiences among experts and practitioners. Concurrent with the SSA special session was ongoing work with the Inter-Pacific Project. This project provided world leaders in the surface wave method a chance to collect, process, interpret, and compare surface wave data and resulting models for a site of known velocity structure. Results from the Inter-Pacific Project completed in 2018 have been used to produce the most comprehensive guide to date on the acquisition and analysis of surface wave data for earthquake engineering. These are the guidelines that we endeavor to comply with. Now let's take a look at an example of a recent project in which surface wave testing was deployed. VS30 was needed at Horse Creek Bridge in Siskiyou County, California, State Route 96, in order to determine seismic site class. Lithological information was provided via soil and rock sampling. This area and lithology are consistent with that of dredger tailings, fat clay with heavy gravel content, transition into silts and sands with a weathered graphite schist contact occurring at approximately 40-foot depth. These subsurface conditions did not lend themselves to drilling, causing difficulties and hole failures. In order to deploy the PS suspension logger without the hole collapsing, the hole would need to be cased and grouted. The grout generally works to ensure intimate contact between the casing and native material, but in this case, and based on our experience with the Smith River Bridge, which was nearly identical site conditions, we knew the grout would almost certainly infiltrate the native material and adulterate any velocity measurements acquired. This is why we decided to deploy MASW and REMI surface wave methods. Here's a look at some of the data that was acquired. This is the real nuts and bolts of the MASW method data processing. On the left, you can see our processing software, GeoGiga Surface Plus. Within this window is the shot record with the trapezoid outlined in red showing the unmuted dispersion signal. Depending on the energy source used for a given shot record, mini dispersion curves are selected and saved. Larger energy sources, such as an accelerated weight drop or 20-pound sledgehammer, will utilize most or all geophone traces to hopefully image lower frequency, greater depth bands of the dispersion curve. Smaller energy sources, such as 3 or 10-pound hammer, use less traces, focusing on high frequency signal near the shot location in order to capture shallow velocities. Depending on data quality and site complexity, anywhere from 50 to 150 of these dispersion curves may be picked. This is why it is important to reduce the time required to pick dispersion curves. On the right of the screen, you can see a spreadsheet that I designed with Visual Basic macros and conditional naming conventions to drastically reduce the time it takes to pick and save dispersion curves. Where a single pick might originally take around 2 minutes without automation, this tool can name and save a curve accurately in 15 seconds. That save time adds up quickly. It's important to note that this video is meant to depict our selection and saving process and is not necessarily the fundamental mode being selected. So what do we do with all these dispersion curves? This is an image of an application that I built that allows us to analyze dispersion curve data with increased effectiveness and efficiency. The program will extract all of the FV files saved in the previous slide. It then calculates the maximum wavelength possible for each curve based on the number of geophones unmuted and trims the data accordingly. The data is then plotted, each curve able to be selected and inspected. Outlying data files or records associated with greater noise can be removed within the web app. Upon completion of data cleanup and analysis, a new FV file can be exported that is curve fitted to the averaged and upsampled dispersion curve. The dispersion curve is then used in GeoGiga for the inversion process. With our newly refined dispersion curve, a velocity structure was modeled. Using information gleaned from both the refraction data and boring logs, an initial model reflecting the graphite schist contact was used to guide the inversion. The gray areas outlining the initial model represent the 30% inversion search area. Below the model is a plot of misfit or RMS error at each iteration of the inversion. It can be seen that the genetic algorithm used for the inversion is making adjustments to the initial model in an attempt to decrease the normalized RMS error between observed and initial model dispersion curve. But after 4 iterations, the fitness plateaus, indicating that the initial model was not too far off. This emphasizes the value of a priori information or data from other methods. In this case, we were able to obtain VS30 with using MASW data exclusively due to the stiffness of bedrock. However, generally, passive measurements should be utilized to confidently investigate below 20 meters, according to the Inter-Pacific guidelines. In order to better understand how the inverted velocity models respond to parameters such as the initial model, Poisson's ratio, and density, another web application has been developed by CalTrans to plot multiple built velocity models along with their associated parameters into a single image. By doing this, we are able to visualize the solution space or range of velocity structures and VS30 observed throughout the modeling process. This information is vital to understanding the uncertainty associated with the non-uniqueness that exists within the primary velocity model seen on the previous slide. Here we can see that the normalized root mean square error between the dispersion curve and inverse model does not experience severe change despite variation in Poisson's ratio and initial model. In this case, we choose the model that best utilizes a priori information as seen in teal. Our improved methods of surface wave analysis now include MASW, REMI, and 2D microtremor array methods in our tool belt. We are transitioning from exclusively size-opt REMI to GeoGiga Surface Plus, a much more powerful software suite that allows the analysis and modeling of both active and passive surface wave methods. Our methods are designed around and strive to adhere strictly to the best practices laid out in the Inter-Pacific guidelines. We have developed programs that allow us to examine and interact with surface wave data to allow increased accuracy and definition of our velocity models. All of these changes result in improved capabilities for non-invasive site class characterization. Moving forward. Although we have internally improved our ability to conduct surface wave analysis, as we move forward, we want to think about how to contribute to the improvement of the method for CalTrans and the geophysics community as a whole. Here's what we'd like to accomplish in order to do this. We want to continue to improve our ability to analyze data through the further development of our tools. We're striving to continue increasing the efficiency with which we collect and pick data. We'd like to fully automate the dispersion data selection. This would ensure that an appropriate frequency range is selected based on geophone spacing, number of geophones unmuted, and source type. This would also help to remove any bias or user error present in the picking process. We want to provide results that clearly convey the nonlinear accumulation of error throughout the process. Internally, we plan to someday have the capability to conduct love wave and two-dimensional analysis as another set of tools in our belt. Thank you for your time and attention. Please feel free to reach out with any questions.
Very good. Thank you, Nolan. Thank you, everybody. Great presentations. Not a huge surprise that we are running over here, but